at SCL, Mohali, Department of Space. Dr. Rajesh Mehra, Head of Department EC and Coordinator of this program. This program participants at NETTR and Network Centers. A very good morning to all of you. The goal of education is not to increase the amount of knowledge, but to create the possibilities for the students to invent and discover, to create the human beings who are capable of doing new things. Well said by Sir Jean Piaget. Now, the destined person to honor us with his presence is Engineer H.S. Jatana. It's my privilege to introduce Engineer H.S. Jatana. He received his engineering education from Beach Pilani and had a brief stint at CMC Delhi as software engineer, wherein he worked on railway computerization projects and later on he joined SCL in the CMOS division. He worked at Rockwell Semiconductor, California, USA, where he was involved in the design of R65 series devices. He has worked in different areas of CMOS and has vast experience on CMOS design, device testing, characterization, test program development on ATE, silicon debugging, process integration, porting of few technology nodes starting from 5 micrometer to sub-micrometer nodes. And he also worked at EMS Austria for 10 months on deputation for porting of SCL schema at the foundries. He has the design of various ASICs and products like energy meter chip, single chip telephone, 12-bit ADC, 14-bit DAC, CMOS imaging sensor, signal processor, SRAM, LDR, LDOs, radiation hardened devices, etc. His areas of interest are low power CMOS design, analog design in DSM, process enhancement, optimization in DSM era. He has initiated many new process development modules like HV, SOI, BiCMOS, CCD process technology with back thinning, materials of group 3 and 4 on silicon for photonics, etc., and APS for camera applications, ultra low power devices, rail to rail OTAs, RHDPs, SRAM, etc. Also interested in spreading VLSI education and has delivered numerous lectures and tutorials on VLSI design and process technology at IITs including Kharagpur, Kanpur, Madras, Bombay, Roorkee, Guwahati, Ropar, Mandi, and various NITs including Hamirpur, Kurukshetra, Manipur, Jalandhar, NITTTRCHD, Pune University, Assam State Technical University, Andhra University, PU Chandigarh, etc. He has also conducted a one-day tutorial at 17 VLSI Design and Test Conference and including VDAT 15 and VDAT 16 at Institute of Space Technology at Trivandrum. He, along with Dr. Puri, G.D. Puri, Head of Anesthesia and Intensive Care, PGI Chandigarh, has 2 patents to his credit for the development of closed-loop anesthesia drug delivery system, which is being used online for critical surgeries like cardiovascular thoracic surgery. Now, the moment has come to add a golden feather in the hat of success. With these words, may I request Engineer H.S. Jatana for his knowledgeable words on the topic of CMOS design.
Thank you, madam. First of all, I would like to express my gratitude to HOD Professor Rajesh Mehra for giving me an opportunity to interact with you. So this particular course is on design of an integrated circuit. So there are 4 lectures which I will be giving. So in the first one, I will be covering the front end part of an analog product, and in the second I will be covering the second, the backend part, the physical implementation of a chip. And then we will take up one example as a test case that there is a standard product which is a 24-bit sigma delta analog to digital converter. And so those I will discuss. And then there is another lecture on some advanced devices. This is what it has been scheduled. So now, what is the basic? Now this particular thing is pertaining to only the analog part. So now we will discuss what is the how we do carry about the analog design. So there is no general methodology, there is no general design flow. Flow is there, but there is no like a specific route, or you can say an algorithm. In the sense you can put the specification and it will generate a circuit. That is not possible. When you do analyze a circuit, there are algorithms, computer can solve it. But if you tell like a program to generate a circuit, that is not possible in an analog circuit. Synthesis is different, where you from an RTL you generate a combinational circuit. That is different, but for an analog it's not possible. So there are various approaches which are used. All sorts of approaches are used in designing these analog circuits. Now there are various levels of abstraction. On the top, if we see like an op amp, let's take an example of an op amp. So op amp at the abstract level, it's just a symbol we use. And but once we go deep inside that block, so there may be around 10 or 15 transistors. And if we go deep within the transistors, so we will have to know about the device physics, about the, so at the top there's an architecture level in terms of transistors, and then within the transistors the device physics, and particularly if you are designing at a lower node, which we call it a deep submicron node, so quantum effects also comes into picture. So this, to be able to design analog circuits or any circuits, so the solid state knowledge of the solid state physics, semiconductor physics, device physics, circuit theory, and mathematics. So all these, a combination of these things are required. And then since the number of transistors are getting increased, and the modeling part is also, there are around 97 parameters of a transistor in HSpice model, which is a BSEM 3v3 or BSEM 6 version also has been released now. So to solve those equations, it's not possible. So you have to use some EDA, some CAD tools to be able to simulate a circuit, to be able to lay out a circuit. You should be able to connect various transistors with each other. And then finally, you should be able to calculate the parasitic value and take parasitic values into effect while doing the simulation, so that the end result works. So this now this involves a very good modeling, the device models of all components, passive and active. So this another, which means the EDA tools, the knowledge of EDA tools, how to use these tools, and how these tools fit in a design flow. This also, there are two lectures which we are covering pertaining to the flow, or while using the digital simulations and analog simulation, how to do. Now in the last 20 years, the trend has been in the CMOS, the scaling means the dimensions, all dimensions, lateral and vertical, they are falling over the last 20 years. So what is the effect on design of analog circuits particularly? This scaling has been done for, it has benefited the digital part, but not the analog part. So let us see in this table, if you are able to see. So we have chosen 0.25, 0.18 and 0.53 microns. So you can see the ion is almost same, 600 at 0.13. It has decreased to some extent, but we can say it is almost same. But see the I of current, which is in picoampere per micrometer. So at 0.25 it is 10, and now at 0.13 it has increased to 320, which is, you can see, is 30 times. So what is the effect of this? What is the meaning of this? Means ion by I of ratio for a transistor. When we see what is the most important attribute or most important characteristics of a transistor, it is the ion by I-off ratio ideally has to be infinite, because I-off has to be 0 and ion has to be maximized. When you design a transistor, you design maximizing the ion. But you 600 is an 600 microampere per micrometer is an ID set, which is an ideal value, keeping in the various implants. You cannot end the mobility at those implants. You cannot have more than this. But ideally, I-off should be very, very low, almost 0, so that an ideal transistor ion by I-off will be very almost infinite. But practically, it is not a good transistor where ion by I-off is 10 raised to the power 5 or 10 raised to the power 6 order is supposed to be a good one. But if you scale down the transistors, ion is we can say it's not falling that much, say 90% falling, but I-off is increasing 30 times. So the overall ratio ion by I-off falls. So what is the effect of that? The effect of that is like you have more power consumptions, you have more leakages even when the transistor is towards the off state. Delay is, we can see, is a big advantage. It is falling, of course. It will fall from a 45 picosecond to 15. So 1/3 delay has decreased to 1/3. And the reason for this is basically your channel length has decreased from 250 nanometer to 130 nanometer. It's half the distance. So now the electrons have to travel half the distance, but the channel is highly now the resistivity of the channel changes because of the doping level. So there is a constraint on the mobility. So exact the delay which should proportionate falling of the delay doesn't happen, because the mobility also falls to some extent, but overall the delay decreases. So this is one advantage in these transistors when the delay decreases. If we go directly to last column, FT, so FT falls, we can see from a 30 gigahertz to 80 gigahertz. So FT is the cutoff frequency. What is the meaning of it? There are two important terms. One is FT, another is Fmax. So FT is a cutoff frequency. So this means where the current gain is both are same ion, the input current and output current is same at a particular frequency. So that is the frequency. As we know, a MOS transistor, the input is a gate oxide. So it won't take, ideally the DC current will be input DC current, which is a gate current will be 0. But since there is an input capacitance, which is a CGS, so at higher frequencies, the capacitance will become very less. So it will take some current. So that will be the input current. And when the ratio of output current, which is an IDS, to input current, which is an IG, is same, or the log of this is 0, so that is the frequency, we call it an FT. So as a thumb rule, you should be able to design circuits which are around 6 FT divided by 60 or 80. So as a thumb rule, the operating frequency can be it gives a fair amount of idea, like by using those transistors, what kind of operating frequency of the circuits you will be able to achieve. Another thing is, you see the fourth row, which is a GM, is very, very important parameter. So GM is a slight increase is being felt from from 0.25, it is 0.3 micro Siemens per micrometer to 0.6 microsiemens per micrometer at a 0.13. So this is one advantage. Transconductance is a mutual transconductance, GM. So this increases. So this is an advantage. All the capacitances, they will decrease, and the reason is your geometries are decreasing, because the capacitance are directly proportional to the area W into L, WL. So when the sizes, when the geometry decreases, the capacitance will definitely decrease. So this is the result which is being shown in these columns also. So your CG and like CGS, CGD, those, and the junction capacitance, the diffusion capacitance, junction capacitances, both they will decrease. These figures are given in femtofarad per gate. VDD is falling, as we have seen, and from 2.5 to 1.2. The reason for fall of VDD is, like, if once you reduce the length, the electric field, if you retain the same VDD, the electric field, which is V by D, it increases. And once the electric field increases, there are severe short channel effects, and to contain those short channel effects, you have to decrease the VDD also, so that the electric field doesn't increase beyond a particular limit. And another reason is for an FT, because the VDD also is has decreased, so that the input level now they don't have to change to a very high level. So then, like from 0 to 1.2, earlier it has to go from 0 to 2.5. So the rise time will definitely be more. But if the input level has to increase from 0 to 1 volt, the rise time also will be comparably less. Another important parameter of a transistor is the gain, intrinsic gain, which is GM-R0. GM increases by scaling, but output conductance or output resistance R0, it decreases. So the overall effect is GM-R0, which is a gain, it decreases, and you can see here it has decreased from 39 to 14. So now what is the effect now if we want to design analog circuits, if we want to design amplifier, so the gain of these like low geometry transistors are very small, like 14. So if you have to design an op amp where you need a gain of say 100 dB or 120 dB, which is 10 raised to the power 5, so it becomes very difficult to use these kind of transistors. So that is the reason. Now in brief, these small transistors, they are good for the digital part, since you get advantage in terms of FT and delay. And because your FT is more, you can design digital circuits which operate at a very high clock rates because the delay is less. And another advantage, since the area which these transistors take, it is less, you are able to put more number of transistors in a given area, so that more functionality is achieved. And your voltage level is also low, so you are able to save some power, because the power is CV square F, it's a voltage square. So you get additional advantage since you are reducing the power, and you are reducing the voltage. So, and the power is directly proportional to square of the voltage. So that advantage you are able to get. But for an analog circuits, because we are interested in a high gain circuits, and the intrinsic gain of a low geometry transistor is a limitation, it is decreasing. And another thing is once you decrease the power, like VDD 1.2 volt, but the noise level is not decreasing, noise level is same, like for a particular transistor, if it is a millivolt RMS per hertz, so that noise will be same, but your top level has decreased from say 1.8 volt to 1.2, so your dynamic range will decrease. Now you can have output swing, which is between the noise, from the top of the noise to the top of the VDD, which is 1.2 volt, and so your output swings will definitely decrease. This means the dynamic range will also decrease, gain will also decrease. Though you are able to make high bandwidth circuits, but because FT is high, you can have a high bandwidth, but you cannot have very high swings, and you cannot have a very good dynamic range. So with these implications, you have to design the analog part. So now we design circuit using MOS. So let's take a brief overview of the MOS transistor. So now, as I told, you have to, in simulation of a circuit, you should be able to know about the models. Now the behavior of the device is a physical behavior. It covers various effects, and like what is the effect of a mobility on doping, what is the effect of a doping, what is a velocity saturation, what is the effect of electric fields, what are various short channel effects, GIDL, DIBL, your HCI, and what is a substrate current, what is the effect of substrate current on circuits, what type of noise, what is a white noise, what is a 1/f noise, what is a thermal noise, how does it affect the behavior of the circuits. what is the effect of the temperature on the MOS transistor, like various parameters, ID versus VGS, ID versus VDS, your input characteristics, output characteristics, transfer characteristics of the MOS, how does they change with temperature. So all these things have to be cleared before we start actual design of analog circuits. And all these behavior is covered, which we call it a model, because the physical is okay, but to be able to design circuit, you need very compact models, very compact equations, so that you are able to solve in a less time. You should be able to analyze the circuit in a less time. That is the requirement. So for those, we need very compact models or compact equations, and it has to cover the various geometry ranges. Spice model, so these are the various models which are being used by the industry. Spice, BSM, right? We are using BSM 3v3 now. BSM 5 has also been released. Philips models, EKV, then SP and PSP models. So these are some of the models, but most common of these are BSM and BSM 3v3 and BSM 5 models. And some people are also using EKV models. They are very compact. They take less time in simulation. A compact model is having the behavior of the device is explained in terms of like very compact equations. And as we know, the MOS transistors has various operating ranges, like from the cutoff, then saturation, then the triode, and all these ranges, inversion, like and there are again 3-4 ranges within the inversion: moderate inversion, weak inversion, strong inversions. So there is not a single equation which can describe the behavior of the MOS in all these different regions. So the objective of the modeling is to have a very compact equation which at least is able to describe the MOS transistor across the various regions and across the various geometry also, depending on the different W and different L. So this is the basic cross section of a simple device, and you can see this is the equation where we are covering weak inversion and strong inversion, and between weak and strong there is a moderate inversion which is not so well defined. But you can see in a weak inversion where VGS is very less than VT, and this equation is it's an exponential equation. The current, which is an IDS, it depends on e to the power VGS divided by eta and VT. So it's just like a base current of a bipolar device. It's an exponential behavior. But in a strong inversion, it is VGS minus VT square, which is a square relationship here. And in a linear region, triode region, where VDS is less than VGS minus VT. So these are the VT is thermal voltage, which is 25 millivolt at 25 degrees centigrade. So these are the basic equations which we can use in a strong inversion. We have to say of mu naught Cox is a technology parameter, and W by L VGS minus VT square. Now for a circuit designer, in this equation, he cannot change mu, he cannot change Cox. Only we can change the physical geometry, which is the W and L, and the voltages VGS. VT is also fixed. It's a technology parameter. Threshold voltage cannot be changed, but you are free to change the voltages, all voltages, gate voltage, drain voltage, your substrate, your source voltage, and you can change the size of the transistor. And VT is fixed, mobility, Cox, all the layers, they are fixed. They are not cannot be changed. So now let us see in a brief about these regions. So first is a weak inversion cutoff region. We will not use the cutoff region is used only in digital design, where it's the transistor is acting as a switch. So we operate the transistors in a cutoff and the saturation region. But for an analog, we operate in the moderate region, the moderate inversion and weak inversion regions also, there are certain advantages in doing so. But so we will see what are those advantages. So weak inversion, it's just like a BJT in the sense that the current is exponential. It is e to the power VGS divided by eta VT, which is a thermal voltage, and eta is more than 1, so it's 1. It depends on the doping, what kind of transistors you have made. So eta depend, normally it is close to 1.4 or 1.5. Now this region, the transistor will be slow in this region. It you cannot have very very high FTs, but the advantage is why this region is used. You get very low power. The power dissipation is very low, and we can get even a moderate speed even in the weak inversions, by where the L is for a short length, short channel devices, we can get reasonable speed in the weak inversion also. But the disadvantage is matching. Disadvantage is matching. Because in an IC you see many transistors have to be connected, they have to be placed together. Those transistors have the parameters, particularly they have to be matched in fabrication. If the transistor doesn't match, then mismatch effect will result in some of the specification getting out of the whatever the desired targeted specifications are. Like you have seen the differential pairs, the differential pair has to be matched. There should not be any offset. If it is not matched, the offset will be created. Mirrors, if you have a current generator, so you will have a current mirror, you will make various current sources based on that. If the transistors are not properly matched, if slight difference in VT, it the current will not be exactly replica of that. It will be. Are you able to hear me? Oh.
They got reconnected.
Okay.
Automatic sound.
That's okay, but you are able to hear me, or just if there is any question in between, you can stop me.
Any of the center can reply. Anand College, Rajasthan. क्या आपको आवाज आ रही है?
कौन सा जबी? ये?
So if you have any queries, you can stop in between also, or you can write on a piece of paper at the end of the lecture. You can ask, or you can stop me during the flow also. So this matching, when you manufacture many transistors on the same die, so matching is very important. If the transistors are not matched properly, then the overall circuit performance cannot be met, particularly in a differential pair, or where like for a 1 nanoampere current source, you have to make many 1 nanoampere. If the transistors are not properly matched, it will not be 1 nano, it can be 0.9 or 1.1 nano. These things we will see, and how to improve the matching, that also we will consider. Mainly the VT in a wafer, you see like in our technology also, it will differ by say 40 or 50 millivolt. So what will be the effect of two transistors which are placed very close to each other? If their VT differs by 40 millivolt, what is the effect? So this you will have to see in the while putting that particular parameter in the SPICE models, and then you have to see what kind of effect it is having, a mismatch of a VT of say 30 or 40 millivolt. Now most of the time most of these designs, the transistor is used in a strong inversion region, and the reason is we get the maximum gain under this. This is the most common region, and depending on the values of VGS and VDS, you can force the transistor in this particular region. And equation is it's a square behavior, like the current is proportional to VGS minus VT square. So this is the triode region. The advantage of, you can see, of a triode region, VGS is greater than VT, but VDS is less than VGS minus VT. So the field, the channel is uniform as you have seen, and current is proportional to VDS, directly proportional to VDS, as you can see here. And for a small values of VDS, for a small, if the VDS is small, we can ignore this VDS. Then ID versus VDS is becomes a linear function, means the transistor acts as a resistor also. So this region is used in for using MOS devices as a transistor, and so you can control the MOS and use MOS device as a resistor, and the value of resistor will depend on the value of W and L, but you have to be careful. The voltage across that resistor has to be accordingly, so that the MOS is in always in triode region. So this is the saturation region. Pinch off starts, as we have seen. This effect is shown, and this equation is square. It's a square law device, we call it, and this is the most common region. And the advantage is you get the maximum gain in this region. And now, so what do we mean by design when we say we have to design an amplifier? Designing of the amplifier means one is the circuit topology. Circuit topology is given in most of the books, but the design means what will be the sizes of those transistors, what will be, you have to find the sizes of the transistor and the operating point, the DC operating point. And the DC operating point will be in terms of VDS, VGS, IDS, and the sizes will be in terms of W and L. So these are the things you have to find. This is what the design mean. So whenever a design is started, certain input things are given, like you have to design an amplifier for which it should be able to have a gain of say 100, and it should the bandwidth should be some 1 megahertz or 10 megahertz. It should be able to drive a particular load, which can be a resistor or a capacitor. So these are the given things. So the key design parameters are, like for example, in a large signal, in a large signal we have the drain current or the VDS and VGS. They both these they will decide the drain current, and drain current will decide the power dissipation as well as the slew rate. If you want the slew rate to be very, very steep, very, very high, you should have a very high drain current. But if you are having a high drain current, then your power dissipation will increase. So these are some of the effects, and wherever you do the the way you bias the drain, the VDS voltage, it will also decide your swings, the output swings, the over voltage, particularly the VGS minus VT, which is an over voltage VOD. How much, as we know, the transistor is on if the VGS has to be greater than VT, but how much greater? VGS minus VT, which is known as a VOD, overdrive voltage. So the overdrive voltage, it decides your output swings. If your overdrive voltage is very high, your output swings will be less. So we will see in some of these practical numeric values how these things are. Now the small signal parameters which are of importance is a mutual transconductance. It will decide the speed. Then the various capacitances like CGS, CGD. Again, CGS, CGD, they are dependent on the geometry of the device, W and L. They will also decide the speed or the bandwidth. Then the output resistance R0, which will define the gain. If your output resistance R0 is high, your gain definitely will be high. If your output resistance is R0 is less, your gain will be also not very high. So these are some of the key design parameters. Now threshold voltage is very, very important. It is given by the technology, and you have to Like these are the approximate values. Say if we take a transistor which is having a channel length of 0.5, so the VTs will be normally close to some 600 millivolt or 700 millivolt, and the power supply is close to 1.8 volt. And this VT cannot be changed, but this VT of a transistor is fixed. But what you can do is you can have a body bias so that the effective VT you can change. So this way, by increasing the VBS, as the last line says, bulk potential increases, the value of the VT also increases for an NMOS. So that way, dynamic VT shift you sometimes you can do if it's required in your circuit. So VT is not constant for all transistors depending on the transistor length. This is the what plot it says. VT is fixed for large channel transistors. As you can see, if the channel length is large, 10 micron till 1 micron, you can see this flow, this graph of VT is almost fixed, say around 660 millivolt. But once the channel length falls below 1 micron short channel effects start appearing, and you can see it how the VT can drop, because if the channel length is low, the VT starts falling, and it can fall by some 50 millivolt or 40 to 50 millivolt, as you are seeing here in this. Why the VT should fall? Because low channel length. This is the because there is a voltage at the VDS, so that also, because finally you have to, what is the VT? VT is a voltage where you have to invert, you are able to invert the charge in the channel, and once the channel length is decreased, it is getting smaller, the drain voltage also contributes in inversion of charge, so less voltage is required at the gate to invert the channel. So that is the reason why VT falls at short channel length devices. So another mu0 CMOS is a technology parameter. This is the current equation only. I have written in a different manner, but you can see this mu0 CMOS. It is directly proportional to GM square and inversely proportional to ID. So for a small values of current, like near weak inversion region, the value of is very small, because if the current values of ID is small, the value of mu0 CMOS will be small, and it rises sharply as the transistor moves towards strong inversion region, and it again falls at large values of current because of the velocity saturation effects. So you can see this is the behavior of mu0 CMOS as plotted with respect to VGS. So our threshold voltage is close to 600 millivolt. We have assumed 0.5 or 0.6. You can see at 0.6. So this is the behavior. Red one is for an NMOS. As you increase the VGS beyond threshold voltage, the technology parameter, which is also mu0 CMOS, so it increases and reaches a top, and after that it starts falling. So why it starts falling? Because of velocity saturation. The velocity is getting saturated, and even if you increase the VGS, there is no effect, and finally it starts falling. And for N and P MOS, both these curves are shown. Before before start of design of any analog circuit, it is essential to understand how these parameters behave with different voltage, because these parameters are not fixed. As you have seen, VT is also not fixed, mu0 CMOS is also not fixed, it varies. So this the behavior should be known. Now let us see GM, transconductance, mutual transconductance. So it affects the gain and speed, gain GM R0, and it in the speed also, in the bandwidth also GM will come. So this is the GM in the weak inversion region, which is an your current will be an exponential function, and it will be ID by eta VT. And in a strong SI, strong inversion region, these are the three basic formulas, or which you can easily get by integrating by differentiating ID with ID del ID by del VGS. You will get all these formulas. So you can see V overdrive. So GM is equal to 2 ID by V overdrive. If you have biased a transistor at a fixed current ID, then your drive VOV will define the GM. So if you want a high GM, you should have V overdrive plus a small value of overdrive. Then you will get a high GM for a fixed ID if your ID is fixed. So near weak GM will be, so for small values of VGS near weak inversion, we have seen the GM will be small. In the weak inversion region, the absolute value of GM and ID will be small, so only low speeds can be obtained. So right now there is a trend to design circuits in the weak inversion region, and the reason is only slow speeds, like a bandwidth can be few hertz only, say some less than 100 hertz bandwidth, but power dissipation can be very small in nanowatts. So these there are many applications where you need circuits which have to operate at low speed, which are low bandwidth devices, but power dissipation is it has to be very small. And many of these examples are the electronics which is used in medical applications, particularly the devices which are implanted inside the body, like there is a device which is implanted inside the heart, and to generate that electrical signal of the heart pacemaker. So the device, it doesn't require a very high bandwidth, but it's a very like some less than 100 hertz, but the power dissipation is very crucial, since it has to be operated by using a battery. So, and the battery must last for 10-15 years, so you have to design a circuit so that the power distribution is very small. So in that, if you design a circuit where the transistors are in strong inversion region, it will consume huge amount of power, so you have to design in a weak inversion. So there are many applications today where the circuits are designed in a weak inversion region also. So in the velocity saturation region, where the velocity is saturated, this means the drain current, first of all, why the velocity will be saturated? If you increase the field, the electron is getting accelerated because of that field, it will increase, the mobility will increase, but at some point the mobility gets saturated, that is the voltage at where the electron mobility gets saturated. So that is a velocity saturation region. In that region, the GM is not dependent on VGS. If you keep on increasing VGS, nothing will happen in this region. And so this is, if you see the plot of GM with respect to VGS, so here also VT is assumed to be 600 millivolt. So you can see the GM. If this is the point, let us take for an NMOS, which is a red curve, and in the weak inversion, the GM will be less, where weak inversion is where the VGS is less than VT, less than 0.6 volt. You can see here, but in a strong inversion region starts here, the GM starts increasing. Now it depends on the overdrive. If you have more overdrive, you can see here how the GM is performing here, and finally it flattens out. So same is the case with a PMOS. So this is a GM plot of a diode connected MOS. So these are the various capacitances which play important role in deciding the bandwidth, CGS. There is a junction capacitances here, and here there is a sidewall capacitance here and here also. And this is the gate capacitance. So gate capacitance also is two types. One is due to gate, another due to, there will be depletion region, there will be another capacitance due to depletion, and there is an overlap, OL capacitance between the drain gate and source gate. So here the capacitance, actually, if you see overall capacitance, there will be one unit capacitance, and then the overall capacitance will be depending on the area, which is W into L. You can see this is L, and inside this figure is the W. So that will be the geometry. So WL and some basic capacitance like WL into Cox. So this will be the total capacitance. So that is why if the transistor is smaller, the total capacitance will decrease. So this is a small signal model of a device. So this is the gate, this is source. So we will have some like GM VGS, a current source here, this one, and in the input side there will be a CGS, gate to capacitance here, and then gate to drain capacitance, then gate to body, and then this is body was also is shown where the current will be flowing from the source to the gate, and we have an output conductance or an which is known as a G naught or a GDS or an R naught or an RDS. Different books have different notation. This, and then we have a source to body and a drain to body. So this is overall, but but starting, I have a point here. If you start with this model, and if you draw a very simple circuit and replace the transistor with this particular model, it will be some effort for you to solve those integral differential equations. So for a learning point of view, the best is you have to start with a very simplified model. In the simplified model, I mean, you can eliminate all these capacitances first and then solve the circuit. Then you have to consider only the gate, source, GM VGS. That's all. This GM VGS and this. Or if you, is it possible to write on the board?
Yes.
No. So I can just show you, because this is very essential if you have to learn analog design.
इसमें की ये है ना जो ड्रॉ, इसमें डस्टर और वो पड़े हैं. नहीं, ये कीबोर्ड वाला ओपन करो. हाँ, इसमें मार्कर और डस्टर होगा. हाँ, ये चलता है.
ये परमानेंट बात करते हैं ना?
नहीं, इसे करना नहीं.
तो व्हाइट बोर्ड हाँ, ठीक है.
आप कैमरा घुमा दीजिए.
So now let us see any. This is source, this is gate, this is drain. So body is connected to source. So this is the model which has been shown on the PPT. This is a complete model, but if you replace, like for example, let us take a very simple circuit. I will draw only the small signal part. Suppose you have connected a source VS here, and this also is connected to ground, and you have connected a load RL. This is VDD, and you want to calculate what is V naught. Okay, so this now you have to replace this with this small signal, and you have to analyze. You have to calculate V naught by Vs. V naught by Vs. But if you do include all these elements, you will not be able to get a feel of the circuit. So the first is you start with a very simple, like you have this model first. This is ground, this is source, this is your gate, this is drain, this is VGS plus minus VGS, this is GN VGS. This much only. So you can see you replace this with this, you will immediately get the value of the gain. So it is very simple. It's very straightforward here. So what we have assumed these are ideal transistors, like in the sense this is ID, this is VDS. So the transistors are like this. They are flat curve, so that there is R naught is infinite. So I am not putting any R naught here. But because of short channel effects, this is not flat, and this is VD sat. The current do increase here, the current remains constant if even the VDS is increasing. VDS is increasing, the current is constant. So then R0, which is a slope of this curve, inverse of slope of this curve, will be infinite. But this is for ideal transistor, but or long channel transistor, this is true. But for real transistor, there will be some increase in current. So these curves will be slightly tilted like this. It will be like this. So this means some R0 is coming into picture because now you have a slope. So inverse of slope will not be 1 over del ID by del VDS will not be infinite. It will be some specific value. So first is this, and then you go to the next version of this. You put that value, which is an this thing. You do like this, which is sometimes known as R0 or G0 or RDS or GDS. All these terms are same. You solve again this. If you do this, here gain will come minus GM R0. If you do this, the gain will come minus GM R0 parallel RL. Here it will be minus GM RL because R0 is infinity. So here it will be RL parallel with R0 minus GM. It will be the gain. So this is the second, and the third. Now this is a, we are not assuming any capacitances. Now you start adding these capacitances. There are capacitances at the gate, at the drain, at the source, and between gate to drain. Between gate to drain. Overlap capacitance, gate to drain, gate to source, drain to ground, source to ground, but source is already ground, so this capacitance will not matter. So those capacitances also you add one by one. Like first you add the capacitance here. So what you will do, you will put a CGS here. Then you do this GM, VGS, and this is R0. This is ground. We have not assumed the substrate effect because this body is connected to ground here. So if there is a R here, then R will come and the body potential will be same. That effect has, then VBS will come. So I am directly shorting it here. This will be drained. So now you can see here. You see in this model, what is the difference here? It will, if there is no capacitance in this circuit, the bandwidth will be infinite. So this transistor, you give any input signal Vs of any frequency here, you will get the output. So you can give any input signal of any frequency. So what is the hindrance? Because there is no VGS here. So once we put a CGS capacitance here, right, and then this capacitance now, if there is a fast, this node, potential at this node has to be changed because this is Vs here, like saying that. So if the potential at this node has to be changed very fast, then only the output will change here at the output. This output will track this. Since there is a capacitance at this node, the potential at this node cannot be changed that fast. So there will be slope. If you give a very high speed signal, it will not get time to change to respond to that potential. So you won't get any output. So that is how the limitation comes in the bandwidth because of these input capacitance. So input capacitance will restrict your bandwidth because your source is getting connected like this, RS and VS here. If this capacitance is not there, whatever VS fast signal, it directly comes here. But now there is a capacitance, and as we know, the voltage across a capacitance with respect to time, it changes like this exponentially. Okay, so V is equal to V0 e to the power minus t by RC, depending on the value of RC. So it will change, but if the capacitance is not there, the voltage will change like this. So there is no delay. So finally, in the physics point of view, means there is basically the electrons have to move from one place to another place, and the movement of electrons from one place to another place, it will take some time. It cannot be in zero time. So that is the reason, and why we call it the gain and bandwidth is fixed, right? Gain bandwidth GBW. So if you want high gain, you cannot have a high bandwidth. The reason is that only because charge has to move from one place to another. If you want high gain means more charge, and high speed means very quickly. So it is not possible. If you want less charge, you can move it at a very high speed. But if you want more charge, then it will be, you cannot move it at a very high speed. So that is the reason the gain bandwidth is fixed. And so so there will be a pole because of this that will restrict the bandwidth. So in the response, if you see, if we are getting, this is your Bode plot where this is 20 log of gain, and this is your frequency. It is showing GMR naught. This is GMR naught. Gain at all level for an ideal transistor. But if you have a CGS, definitely at some point you will get first pole, and at first pole this start falling by 20, like this. By 20 dB, the gain starts falling at 20 dB. So your bandwidth is only this frequency, and this frequency can be calculated. And next, there will be a capacitance at drain to body also. So in the next, you put this capacitance, which is VGS, and then this is GMVGS, and then this is R0, and then you have put this CDB. So there another pole will come because of this CDB, and since this dB is less than CGS, so this pole will be further away, maybe at here. So at here another 40 dB fall you will see in this. Okay, so this way you keep on adding. Now there is a third. Next you go to the next. You have to put another capacitance, which is CGD. Now this is a Miller capacitor because this is connecting input and output both. So this capacitor can be split in two parts, CGD. So CGD you multiply by the GMR0, and you can bring this capacitance to this side, and you can bring that capacitance that side. And then these two circuits becomes independent. You can write the nodal equation and solve these circuits. So this way, if you try to analyze, you can it becomes easy for you to analyze the circuit, and rather than going straight for the complete model. So these are some of the values of the capacitance. I will skip these things, and output resistance we have talked, and which is 1 by GDS. In some book they call it resistance, in some book they call it output conductance. Both are same, and for long channel devices this is almost infinite, but this is not the case for a short channel devices. So this you can see here how it varies with respect to VDS, both for an NMOS and for a PMOS. Another thing which you are observing, this is the green is the PMOS. So R0 for a PMOS is high. So the gain GMR0 for a PMOS will become high. So wherever you want high gain, you can use a P device. This is at a length of 0.5 micron. So intrinsic gain, if you see, this is the intrinsic gain, GMR0. So it becomes high at some particular point. And as I told you, for a PMOS, the internal gain is high as compared to an NMOS. As you can see here in this graph also. And now, you see, now there is another figure of merit, which we call it a GM by ID. It's a very important design parameter, and it unit is 1 by V. So this means now the question is, if you want to have a high gain, so you should have a high GM. GM or not, you should have a high GM. So how you can have an high GM, high mutual conductance? There are two ways. Either you can have a very high, if L is fixed, you can have, because GM is equal to mu naught Cox VGS minus W by L VGS minus VT. So if L is fixed, to increase the GM, you can have a high large W. But if you have a large W, there's no problem, you will get a good gain, but your bandwidth will fall because the capacitance is directly proportional to W into L. Another thing is you can have, because GM is directly proportional to mu naught Cox W by L VGS minus VT. So for a high GM, the VGS minus VT term is coming. VGS, VT is fixed, so you should be able to have a high VGS, then only GM will be high. That is okay, but if you have a high VGS, means current is also high, ID is also high, so your power consumption is also high. So, but our goal is we want to have a gain where the power consumption is also minimized. So that is why you divide both these, GM by ID. You maximize GM by ID. So you will get the more efficient design. So this we try. So what is the technique? How do we design where we can maximize GM by ID? So this particular thing we will see. So this is what we have plotted. So GM by ID we can have maximum 20 and at a very low VGS, but at a very low VGS our bandwidth will be severely limited. It will be very, very less. But if we want to have a reasonable bandwidth, so we have to design at VGS close to 0.6, 0.7. You can see this region where normally we design with GM by ID close to 10 to 15. You can see here 10 to 15. And here our overdrive is close to 200, 220 to or 200 millivolts. And where we get reasonable bandwidth. Here you can have, okay, GM/ID is very good, but your bandwidth is not very high because you are in a weak inversion region in this VGS. Okay, so this is the unity current. This is the bandwidth FT. You can see this also gives, this is an overdrive. If you increase the overdrive, FT will be more. Or if you decrease the L, it's square. If you decrease the L, your FT increases. So these things are GM by CGS, all this is inversely proportional. So these are the set of equations. You can see here FT. So now how will, basically this is the summary for long channel devices, for short channel devices. Long channel devices, overdrive voltage will be 2 ID by GM, VGS minus VT will be this, it defines channel pinch off. And for short channel devices, V overdrive is not exactly VD-SAT, it is more than VD-SAT. Now, what is the basic design approach now? So how do we start with the design of the circuit? So as I told you, any design, they will give you the objective, like you have to design an amplifier which has a bandwidth of this. It is supposed to drive a particular load. You cannot design any circuit which can drive any load. You have to specify the load. And you cannot design any circuit which has infinite bandwidth. You have to specify the bandwidth, right? For very, very simple analogies, like for a vehicle, you cannot design any vehicle which can carry infinite load. It has to be some 1 ton, 2 ton or 5 ton. Similarly, you cannot design any vehicle which can have infinite bandwidth for circuit. For a vehicle, it is speed. It has to be 200, 300 or 400 kilometer. Speed have to be defined. Load has to be defined. So similarly, in the circuits, these two, bandwidth and load, will be given to you. Straight way you put this in this formula, you will get a GM. 2 pi f UGB. UGB is the bandwidth multiplied by 2 pi will, a factor of 2 pi will come, and you will get a GM. So if you have to design an amplifier, so this is the GM you should have. So now you have got a GM. Starting point is there. Now you have to start GM formula. You see mu naught Cox is fixed. W by L, VGS minus VT. VT is fixed. Now what are the variables? W, L, VGS. These three variables you have to decide. Now it depends on you. You can either pick a small L or a large L. For a short channel devices, you will get high FT. For a long channel, you will get large gain. So you can, and length also affects the noise corner frequency also. Okay, so normally what we do is, based on GM, we will put the VGS minus VT. VGS minus VT is the overdrive. So we will decide overdrive. And VOD is also, there is a limit only, like you can have between 200 millivolt to 300 millivolt. You can choose any of these values. You cannot go beyond this 200 to 300 millivolt. Now GM is also known. V over, you first choose to 200 or 220 millivolt, you will get ID. Okay, and if you want a large V overdrive, you will get a high FT, but you will not get the signal swing at the output. You will get small signal swing. If you want a large signal swing at the output, you choose small overdrive. You will get a large signal swing, but you will not get a large FT. So depending on these, normally in a design there are iterations, many iterations. So you start, as I told you, GM is fixed. You start with an overdrive, say 210 millivolt overdrive, and calculate all other parameters. You can calculate ID from here and proceed further. Once you have got an ID, you know a GM, you know the overdrive, you check for slew rate, you check for power consumption, and you, based on, you have now ID, you have fixed some L, you fix a L, and you find the W from the spice plot, and do find calculate slew power. If they are not meeting your spec, again you go to the first level, you change your overdrive, tune it, and again repeat this exercise again and again. So in few iterations you will be able to do this. So these are known as spice plots. So they are the plots plotted between, you can see here, overdrive and ID for different values of W. So this is a spice plot for a W of 50 micron, and with you can see here with different lengths, the 1 micron, 0.5 for N and P. So for different L you plot this. So what you have to do is you have plotted these curves for different L. If you have chosen an L of say 1 micron for a PMOS, which is a blue curve, this curve for a 1 micron, and you have chosen a V overdrive of 0.25, so VOV of 0.25 and ID, so this W will be 50 micron kind of will come. So this way you are able to do this. So this is the complete flow. First of all, system, because this chip will be used in any system. So from the system specification, you have to drive the circuit specification. The circuit specification, the large parameters like your biases will be derived, and your small signal parameters like gain also will be derived from these specifications. And then you have to choose a topology. You have to partition the circuit, then your basic analog, and you have to do some analysis. We will take this example like see, these are the various common analog structures which are used: common source, common drain, common gate, diode connected transistor, cascade, folded cascade. All these different structures are used, differential pairs, in making the current mirror and cascade mirrors. So by circuit partitioning, I mean this is a example of a differential amplifier. If you analyze this, you will not understand what is the function of each transistor. So you do the circuit partitioning. So here the critical portion is this is the GM structure, red. M1 and M2, they are the differential pair, and these have to be properly matched. And what is this? This is the bias structure which is giving this bias current MB1, and this MB1 has to provide a bias current for M1 and M2, and this bias current is taken from I bias and with this particular transistor. So you have to adjust the WL of this and this, so that whatever bias current you want, you can generate from this I bias. This is the load. This is the load structure. Okay, so now your the GM of this M1 and M2 is important in deciding the gain of this transistor, whereas these are for biases only. And these here, the output swing also will determine the VOD at this particular. So the gate voltages at this point, VGS, will decide those. So this is the circuit partitioning thing. So GM structure, it converts input to an output current. So common source, these various two stages you can use in this. And you can have, this is a single stage amplifier, you can have a two-stage amplifier. So first stage and second stage will be your common source and a current bias current mirror. So you can have bias structure. GM structure requires a current bias I think any cascode structure requires a voltage bias and all these things. I think I will skip. So basically is from this is how you derive the specifications from the system level to the various circuit level, and from the circuit level to the load to the GM to the bias, and you make a series of amplifiers. So depending on the system requirement, all these specifications will flow with each other. So this is how you derive these specifications, and this is a very basic formulas like GM R naught, gain bandwidth will be GM by 2 pi CL, and phase margin will be, you can see, you can calculate, you need not use the simulation, you can calculate these with these simple formulas which are, and overdrive output swing will be supply minus overdrive, and your whatever currents are flowing, this summation of all branches current is the total current, and power slew rate will be I out by CL. Like if you want a high slew rate, CL is the load capacitance is given, then I out, what is the last stage? Last stage means this stage, this stage. So this is the last stage, this will be driving a CL. So the I out of that has a direct bearing on the slew rate. Okay, so and you similar in the same way you can calculate the noise. You have to refer the noise to the input side, and you can calculate the offset. You can calculate all those rejection ratios by these simple formulas. And this is the one example. You can see this is M1, M2 here. PMOSs are used because I want more GM. So this is the biasing network. Bias is obtained from I bias, and this is the active loads, this MB1, and no, so this is the bias, and this is the active load, and here another stage is there, and this is the CL. Now the slew rate will depend on this current I2, because this I2 has to feed to CL. If you want a high slew rate, this you have to make I2 very, very high. So you can see here the what is the current consumption, I1, I2 plus these are the branch currents, I1, I2, and another current I bias. So this is the total current which is flowing from VDD. So you add these current, multiply by VDD, this will be your power consumption. So what is the gain output resistance? You can see here output resistance by looking at the circuit. You can calculate. You can see R out will be GDS 12 and GDS 34 at the one stage. So it's a very simple at the one stage. So here the output of this is taken here. So here what is the output you are getting? A GDS 1 means M1 and M2, they are exactly matched transistors. So what will the output here? You will get a GDS of M2 or M1 and GDS of M4 or M3. So these are matched because the same these M1, M2, M3, M4 are matched at this point. And similarly, what will be the output here? Output resistance. These two transistors will come into play for the output. So this is why GDS 5 and of this. So now you can have a common mode input range, means what is the minimum and maximum voltages at this level which you can give, assuming this VDD. You see, you have to keep in mind that these transistors, all these transistors, this and this should be in saturation region. Okay, so now you see here, you start from here. For this transistor M3 in saturation, what you have to do? So this is VGS here, and gate voltage is connected to the drain. So VGS should be more than VT. So this, what should be the potential at this node? It's not coming. Yeah, here, what should be the potential at this node? So this point should be at least, this is VDS. Okay, one VDS above. And now what should be the voltage here? Another VT, because this is VGS, right? This is gate, this is source. So gate should be 1 VT above, and this is VDS. So this is the minimum voltage you can give here from ground. You cannot give zero voltage here. If you give zero voltage, what will happen? These M1 and M3 will not be in saturation, right? So you have to give a voltage which is higher than zero. Similarly, if this is VDD, and what is the higher voltage here which you can give? You have to make this particular these two transistor in saturation. So that way you have to decide all these by looking at these pictures. So this is what we are seeing. So this is a minimum voltage, and this is a maximum voltage which you can give, which can decide your common mode thing. It is like not very difficult to understand, and you can see here, like let us say this formula, minimum voltage is VSS. This is VSS, which is ground. Then you will have VGS of 3. VGS of 3 is there. You can see VGS of 3 and 4 are same. VGS of 3, and then overdrive of VT, and VGS 1 of 2. Right. So this voltage VSS, if this VSS is 0, then it will be 0 only. So this transistor you have to make in saturation. What is that? VGS is required. Then this transistor you have to make in saturation. VGS of this voltage plus overdrive. So these three you will add. So this is how you will calculate slew rate, input referred noise, and CMRR, PSRR. CMRR you can see depend on GM by DSB, and PSRR by this. So all these parameters you can calculate, and then redo your dominant pole. That all it is also very easy to see what will the dominant pole, and because the dominant pole will be decided by the CC, will be decided by this node. So here this node, this is the CC, and whatever conductances are coming at this node, which will be the GDS of this transistor, and GDS of this transistor will add up in multiplying with this node. So this will affect your first pole. So this is your first pole R out, and a gain of the second. So this way you can decide all these parameters, gain, bandwidth, and rest of the things. So here again the same. If you partition the circuit, it becomes clear. This is the differential pair, this is the load, this is your biasing, and this is a common source. And you can, here P are chosen. You can have a choice of n MOSs here. If you have NMOS here, you will put a PMOS active load, and bias you will put down here, and here also you can have, then a PMOS will come here. So depending on your requirement, you can have these. So these are the derivation of specification. Like differential pair will decide the GM12, GDS2, CMIR, noise offset, gain, bandwidth. They are dependent on M12, right? And this load, the stability of gain, noise offset, this will depend on load, and a common source will decide your gain, output voltage, and stability. So these three, each stage will define something, and current biases will also define CMIR and the voltage range. So each stage will define some basic things, and based on this, so this is the design sequence. So you will be given a slew rate, and based on the power consumption. So because here what is given to you, you are given, you have to design a circuit which has a bandwidth, which has to drive a load, which has a particular slew rate. So based on these slew rate, you define some, you start with some initial values, you put those values in the differential pair, and then in the load circuit specifications will also come based on this. And since you have to decide the value of over VOD, so VOD will depend on the output swing, whether you want low or a high, and gain already has been defined because GM already will come into the picture, and you adjust these values, and then finally you calculate CMRR, PSRR, noise, and if it is not making, then go again here, change the VOD, change a little bit TL, and again do this calculation. So you keep on repeating all these steps till all your parameters are chosen. So as a thumb rule, some of these things are given, like CC you have to choose. So what if your load is given, you have to choose 0.2 times the CL, or 1/5 1 by 5 times of CL, you have to choose this compensating capacitor to get a, normally the phase margin should be between 40 to 60, or no, preferably 50 to 60. If you are able to achieve that, is better. And so normally IT is around 10 times than the I1. The first whatever the current in the first stage, the second stage normally is around 10 times to meet the gain and stability. These are just as a thumb rule, not fixed values. So this way you can calculate, and this also again it's those steps only are written which I have explained to you. So you can see this, the gain of GM1 5, if you GM5 transistor and one transistor, this is how the curve, the if you want to have 60-degree of phase margin, so you have to follow this red, most of these red paths. So you should have GM fifth transistor and one transistor should have a ratio of 10 almost, then only you will get close to 60. If it is 5, then you will get like below 60, but above 60 you have to have this 10 kind of thing. And if you go beyond 60 here, it's okay, the phase margin is getting improved, but your GM is like GM5 has to be very very high. GM high means again your then ID will shoot up. And so though there is a compromise, you cannot get all these parameters good, so you have to finally a compromise is there. So that is how you have to choose these biases. And this things, these are some of the excellent books, which is one is a Behjad Razavi, another is Allen Phillips, Allen Hallberg and Douglas. So there is one paper also. This is a very good paper. So you can refer to, it's an IEEE journal, and where this methodology of designing is given. So any questions now?
Any query from any of the nodal center? Anand College. Who man, do you have any query? SGT Gurgaon. SGT Gurgaon, sir, do you have any query? Any query from your side?
Any question on college?
Please say yes or no. Mani College. SSIT Dera ma'am, do you have any query? Okay, sir.
Thank you so much, sir. Your session was full of passion and priceless information. We'll resume here after a short break
And time.
at 11:30. Welcome back. Now we'll start with our next technical session on analog CMOS design. For this, I would like to invite Engineer H.S. Zatana to please proceed with the session.
So, going further to in the first part, we covered the front end part, how to make how to fix the circuit values, how to decide the various large signal, small signal like VDS, ID, WL, GM, slew rate, SMRR, and things like that. Now this is the design flow. So we start with the design specifications are given, then finalize the architecture, and then do the schematic entry and complete the circuit. And if the specifications are met at the front end level, at the circuit level, then we will go for the physical implementation. Physical implementation is how the devices or how the various elements will be fabricated, how they will look how they will look physically, which is also known as the layout. And after doing the layout, we have to verify that whatever layout we have done, it is matching as per the circuit. And there because of interconnects, there will be some parasitic, so we have to calculate those parasitic and effects, and then again we have to simulate the circuit, taking into consideration various RLC parasitics, and see whether the specifications are meeting or not. If the specifications are not meeting, then either you change the layout, or you may have to change the architecture completely also. And if the spec is meeting, then finally you go for the chip finishing. So there are many things in the chip finishing also, like putting of the IO pad rings and dummy fields, corner fields, and then finally a GDS is released. So what is layout? Layout is creating geometries. Earlier we saw that W and L are the two geometries of any passive or an active component. So we have to define those and we have to create those. So from the from the layout, we will get these various polygons, and these polygons, they are used in generating the masks, which is in a format known as GDS, and all these masks, they are used in fabrication of the device. So this was the circuit which we discussed earlier. This is an op-amp, symbol is given, and this is how it looks if we do the physical implementation. So here, this is a VDD top, and this is VSS, and you can see here now this is the VN. So this is one transistor here, VN, and this is another transistor which is a differential pair. So this one and this one is forming a differential pair, and we are taking the output from here, V out, and this is a VB. This is the biasing part of these transistors. So these shows, you can see various colors and various polygons, and these polygons, they represent some layer. So we will see these things. So this is in a typical simplified CMOS process. It's a single well process. So there will be some color like this color for a P well, green for N well, and there will be, first we have to define the wells. In the wells, we have to define the active area and field area. So these will be like in this is a mask. If it's a positive mask, wherever this square polygon is coming there, P well will be formed. So P well in the sense, in this particular side, the boron will be implanted and that area will become a P. And within that area, if this is P, I will make N transistors here. So this whole thing is P. Rest of the area which is white in color, it is unchanged. So in this area, some portion I will define active area, which is green in this shade. So you can see this is smaller than this. So there will be some active area. And in this active area, we will define the transistor. Active area is the area where components will be made. The rest of the area is a field area. And this is the poly. You can see here. So this is the polyline polysilicon, and below this will be an GOX, gate oxide. And then both sides will be diffusion masks, and diffusions are not shown here, but how you can see, you can take this line, put on this here exactly. So other side of this line will be a source drain diffusion. So this is how active area, on top of it is a gate mask. So this is how it comes, and then finally you have to make contacts. You can see these are the contact. This one dot you are seeing, it is on this line, it's a gate contact. And as I told you here, this transistor, you see this is a diffusion. The definition of transistor is a poly which will cut the diffusion. That is a transistor. So diffusion will cut. So this polyline, it is cutting the diffusion, so it becomes a transistor, and you have to make contacts as we are making contacts here. And then finally by metal you have to connect these. And if there are two metal, you take a via and go to the second metal and things like that. This is a very simple explanation. If this is a wafer, this is a mask which is a quartz plate, and there is a quartz glass and a chrome pattern. Here this was the area through which the light will pass, and it will, you have defined this area. Now you have defined this geometry. This is a photoresist. Depending on positive or negative photoresist, one will dissolve, and you have defined this geometry. If you want to like do some boron implant, then after that you do an implant. What will happen is this area is open, boron will go here, and this area photoresist is there, and the boron atom will be stuck in this photoresist only. They will not go in the wafers. But here, since this path is open, they will directly go in this. So this is how it fabrication is done. After the end of the fabrication, this is a cross section which you are seeing. This is a P silicon, this is a P well, this is an N well. So let's take this N well. These are this is a P well. So these are N diffusion. This one, this is N diffusion. This is N diffusion. This is contact. Okay, this brownish is contact, and this blue color is a salicide to improve the resistivity. This thing is a gate. This one, this color, gate oxide. This is poly. This one, yellowish. This is poly. This is the contact. Brown is the contact. Again, this is a salicide. This is a via. So it's going top on top of. So this is one transistor. This is another transistor. This is Fox. This particular thing. This one, which you are saying. This also is an oxide, and this particular thing separates these two things. You can see here. So this is another transistor here. This is another. So this is the separation. So similarly, this is another transistor. So this bluish can be cobalt salicide also, or a titanium salicide also. So there are 2-3 things, metals which can be used. So in a modern, they have more than 200 processing steps, and this is a 3D view of a transistor. So this is a bulk, this is length, this is W, this is gate. Now from the top, if you see, this is source, you will make contact here, here, here. Drain, you will make contact here, here, here. But this gate, normally we don't make contact here on this, since below the gate is the This is a reddish color is a poly, and below this will be a gate oxide. So we don't want to harm in any way this gate oxide. So normally outside this square, this area is a active area, and outside this area is there will be a um, field oxide or a shallow trench isolation, which is just for isolating. So this gate will run over that isolation, and there we will make contact. So this you can see here. This is a cross section. Okay, and these N and PMOS for a CMOS both have to sit together. So this is Fox. Now you see this is a P substrate. This is a P. So you have taken a P contact, P plus. You have taken a contact. These two small squares, they are a contact. In this area, there will be active region. Whole thing. There will be active greenish, and then this active region will be cut by this reddish, which is a poly line. Then it will become a transistor, and then you do the implants and both sides, and then you take these contacts. So you are taking contact source drain here, 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 and as I told you, this poly is going on the field region also. This area, this is field, so you will take contact here. So this same way here, except there's a P substrate here. It's an N well, so you have an L well. So this is an N well. On the top view, this is cross section. So you have an N well here. This one. This is an N well. Okay, so this is W, this is L. Okay, so this now, what do we mean by design rules? So the design rules, you see the thicknesses of the layers. This is the cross section. In the cross section, there are various layers, various thicknesses. That is a part of the transistor definition. This is a process that designer cannot change. On the top, you have these polygons. You can alter the shape of all these polygons. That is with you, but there are certain rules like what should be the minimum L, what is the contact size, what is the one contact to contact distance, like what is this contact to this distance, what is this edge to this distance, like this. So there are various rules you have to do this, and these rules are based on, because if you make two lines so narrow in fabrication, it will not be possible. There can be either shorts or opens. So keeping in the fabrication manufacturing process in mind, these rules are defined. So these are known as the design rules. Okay, so these are all design rules can be categorized in 4 different, like what is the minimum width, what is the minimum space, what is the extension, what is the overlap, what is the extension. If some layer is coming over the top of that layer, so then it has to extend so that there is a proper connectivity between the 2 layers. So we will see some of these. You can see here it's a 2 is the width. You cannot have a like in a 180, you cannot have a width which is less than 180. Then there is a separation which is known as a spacing rule. So 2 polylines can be separated by this minimum of the maximum can be more, but you cannot separate these 2 lines. And then this is a well. Then this distance where 2 is written, that is a minimum width, right? Minimum spacing to well. And this is also minimum spacing within the well and outside the well, which is wall. So these are the spacing rules. And these are the extension rule. You can see if you are making this contact, if you make this contact towards this side, almost at the edge, what may happen is during fabrication, this edge might shift slightly here. So the contact will not be a proper contact. Your contact resistance will be very high. So that is the reason you have to make this centered contact so that there is sufficient enclosure on all these sides. So these rules are so proper extension. These rules are kept in mind by doing this. So software will check for design rule, then electrical rule will check our proper connection is there, and some then whatever circuit you have designed, the schematic is matching. And then there is antenna rule also in lower geometry, which is not mentioned here. It will check for antenna. There is no any antenna on gate is not formed, because that can spoil the gate. So now we will go through quickly in how to do the layout for all these passive active components. Resistors are widely used in analog designs, but the question is the tolerances of these resistors. They are very poor. Like resistance value can vary by as high as 20 to 30%. If you are making a resistor of 1000 ohm, it need not be 1000, it can be 700 or it can be 1200 also. So what you have to do, but matching the resistor is very good, in the sense if two resistors are placed close to each other, though you wanted in the design the resistor value to be 1000, but if it is 700, but both the resistor will be close to 700 only. This is what we mean batching, if they are placed close to each other. And by trimming of these thin films, you can make some resistor close to the value. But as a thumb rule, since absolute value of resistor can vary, so normally a ratioed resistors are used, like R1 by R2, and that will not vary much. So now you in a pure digital process, the value of the resistance, if it vary, doesn't matter. But for an active, but for an analog, the value of these resistors matter, and these resistor has to be linear also. So you can see this is a resistor which is made of N well. This is an N well. You make contact here, you make contact here. So one contact is here, one contact is here. This is the top view. So depending on this distance, the value of the resistors can be found. This is how it looks. So this is the complete well, blue. You make one contact, you make one contact. So now this will be L, this will be width. The current will flow from like this. Okay, so this will be what will the value of this resistor? There is a value of, there is a fixed resistance of these two contact. So this will come to R contact, and then since this is a diffusion, there will be some sheet resistivity which is RSH, then RSH into L divided by W. So this will come from R is equal to rho, that R is equal to rho L by A. So what is A? A is because this is the thing. So this is W, area of cross section, W into thickness. So that area of cross section will come. So based on this thing, you can see here. So R is equal to rho L over A, and rho over T we are defining at a sheet resistivity RSH, because that is not designer cannot change, it is fixed. Designer can only change L and W. Sheet resistivity is a property, it is a property of the process. So rho by T. So you have L and W, so you can adjust L and W. Sheet resistivities are given, so you can find this R. So normally if L and W are equal, so R is equal to R SH. So L and W are same in square. That is why sheet resistance, sheet resistivity is given in terms of resistance per square. So that is the reason for this. So these are the, you can have a P resistor, poly resistor, N well resistor. N well, this is a well, you are making two contacts. P resistor, in a well you have a P diffusion. You can see this is a P diffusion, and you are making two contacts. Poly, you have a poly and you are making two contacts. So what is the difference if you see? Let us take this one. If you have an L, N here, P here, there will be some diode here, reverse biased PN junction. Okay, so because of this, there will be some depletion region also in the N. So N, this width will decrease because of the depletion region, depending on the voltage between across the two end of these resistors. So this resistor is not a linear resistor. There will be some voltage coefficient. So the value of the resistor depends on the voltage. Another thing is, since there is a PN junction reverse biased between this N well and P, there will be a current flow through this resistors, and Third is any noise at the substrate will be put inside the resistor, and any noise from the resistor can get transferred to the substrate, which can get transferred to other elements also. And you see here, if you see, what you do is you have an N-well here. This is an N-well. You make an N-well contact and you make some DC value. Put some DC value, like it's an N-well. So normally N-well you put at a higher value, say 2 volt. You connect this. So now you have a 2 volt wall here. So this this resistor is sitting here. So it is protected from interference of substrate now, because there is a you have shielded it, just like a coaxial cable concept. So this is a shielded resistor. So you have protected this resistor. But again, it will have some VCR because of depletion. Poly also have a poly depletion, but it is quite less. The VCR is very less. And this is a Fox field oxide. So the depletion will be very less. But the question is, if you have to carry a huge amount of current, this is a field oxide dielectric. This also is a field oxide dielectric. So this resistor is sandwiched between two dielectrics. So heating properties, heat dissipation properties are too bad. So you cannot dissipate much of heat. Whereas well resistor, the complete well is there to dissipate heat. So each of these, in fact, there are some 5-6 positive, 5-6 disadvantages of using these resistors, and where one is to use, it depends. We will not go much detail in this. Now, you see, if you have to have a resistance of, say, 1000 ohm, sheet resistivity is, say, 10 ohms per square. So 1000 ohm means you divide 1000 by 10, so 100, you will have 100 squares. This means W by L will be 100. In one dimension it is 1, on another it is 100. So you cannot produce this big line where aspect ratio on one side, one dimension is 1, another 100. So it will be this line, it is not possible to produce. So what we have to do is we have to make it a serpentine. Yeah, like you cannot have long strips. So what you do, you have like this. If 100 means 1, 2, 3, 4, 5. So this is 20. So this width is 1. This is 20, 20, 20, 20. You make it 100. You make it serpentine like this. So effective resistance from this point will be now 1000 ohm only, from this point to this point. So now there is one way like this. Another way is you can have a sectioned here. What is the advantage? You have one segment 20, then you have a contact, then here you have a contact, then another. You have contacts here. You see which one is better. If we see from resistance point of view, this section is better. It will give you exact, because the reason is here you have corners. Where there are corners, they cannot be modeled properly. So here there is no corner. It's a line. It will have sheet resistivity, then contact resistance of these two contacts will come, and they are connected with metal. Sheet resistivity is very small, whereas their corners are there, so this cannot be modeled. But only thing is, here it will take more area, since design rules will come for all these contacts. You cannot place this very close to each other because of design rules where this can be placed to each other. So it depends on your situation where you use what. Now capacitance are also quite commonly used. One of the simple capacitors is a MOS capacitor. You can see you connect source and drain together. This is one terminal, gate is another terminal, so it becomes a capacitor like this. But the behavior of this capacitor, depending on this voltage across the terminals, which is a gate to body voltage, will be like this. Okay, so you can use this. It's a non-linear first, as you are seeing this. So you can use an accumulation or a depletion region. So it has limited range. Or otherwise you can have a proper capacitance where with two metals or two poly and with an oxide, that also is possible to have. And you can have a poly capacitor or a metal nowadays MIM they call it, metal insulator metal capacitors are used. They are better than poly capacitors. This is how it will look. So this is the cross section, this is the top view. So you can see this is one plate, this is another plate. This is the top plate, this color is blue. This brownish is the bottom plate, bigger. We are taking contact at the top. This is the contact of lower plate. This is the contact of top plate. So capacitance will be this one. If you see here, so this is the bottom plate. This one, this if you see, which is brownish in color, this is the bottom plate, and these are the contact outside perimeter, right? And this blue is the top plate, and these crosses are the contact. So capacitance area, this much area, because the bottom plate is bigger, top plate is smaller, and the capacitance will be calculated area. Top plate will be calculated, and there will be some fringe capacitances. That way you have to model. There is a parasitic of bottom plate to substrate CB that will come. So some parasitic capacitance will come, which is 4 to 5% of this. Now this is a MOS transistor. So this is the layout, drain, source, gate. Okay, so you make these contacts of drain, source. This is poly, like this, and this is body. Now again, if you do the connects like this, of a drain source, you have put one contact, one contact. This is not proper. What is the reason? Because your drain area is this much. Okay, like there will be some diffusion in the resistance. This you have not taken into care. So this diffusion in the resistance will come. So what you have to do is, if you put this one contact resistance, say 10 ohms, so you have put 3. So what will the contact resistance of 3 contacts? It will be 3 are coming in parallel. So you have reduced the contact resistance. Whereas if you do it here, there will be 10 of this contact, and this area will also lead to some resistance. So this resistance will directly come in drain or source. That will affect. Okay, diffusion resistance will come. So you can, this is a better layout. Now, same way, this is the W. You can see you should try to put as many contacts in the drain, as many contacts in the source, as many contacts in the body. The reason is you are decreasing the contact resistances, the parasitic ones. We will see again further. You see, if I am having a particular W and this is L, I have a very elongated resistance. So you can calculate these capacitances CSB and CDB. What will be CSB? This W and W into L. L is this much. Okay, so now, but you can split, say this W by L, it will have some ratio, you make it half. You do like this. So exact W, you have make it half. So you have made 2 transistors connected in parallel. Overall W and L will be same, because this will be W by 2, since you have connected in parallel. But now you see what is happening. Your CSB will reduce to half. How? Because you see, this is poly, this is drain source of one transistor, this is poly of second transistor, this is drain source of second transistor, and this source is being shared by these 2 transistors. So the capacitance will be W by 2 into L. So it is becoming half. Right. So you can see in the layout, you have reduced one capacitance to half. Similarly, if you do, you have, but other capacitance dB is not changed, because drains you are seeing is twice here. But if you split in 1/3, if you make it W by 3, you can see CDB 2 by 3, and this also 2 by 3 you are able to do. So this you have to see how many fingers. This is known as a finger. So you are connecting these 3, or this. In circuit is same, but layout is different. It will make lot of improvement in the circuit performance. So this is how this layout is very, very important, how you have to do. Now, matching means where, like a differential pair, each resistance, each particular geometry has to be matched. So then the precision of the device, where the devices are occurring in pair, that will change. So sometimes you have to use devices of different shape, and direction also has to be same. There may be use of dummy, and there is something known as a common centroid. So we will see those things. Let us see. One is interdigitated layout. It minimizes the effect of process variation. You see here, I am having two resistors, A and B. Okay, so I have split A in how many parts? Three parts here. So one, two, three. So I have two options now. What I can do is I can put A1 here, A2 here, A3 here, B1, B2, B3, A1, A2, A3, B1, B2, B3, and you can join easily. But the question is, what happens if there is a process gradient from this end to this end? Since the A is coming first, it will see less process gradient, these three segments, and B is coming after that. All three segments will see huge process variance, right? Like this can be explained easily, very easily on the board. Now you are taking this resistor. So 1, 2, 3. This is one resistor A. Another resistor you have placed here. Which is A, which is B. You see, if there is a process, normally in a wafer, when you manufacture, there can be some process gradient. Like if we are doing some implant, some dopant. So dopant, if it is uniform, it does not matter. But if there is sometimes it is a gradient is there, right? So this means whatever you wanted to do a implant of 10, but there is a gradient, it is increasing linearly. Say, so here it is 10, 11, 12, 13. So normally 10, so 1 is extra, 2 is extra, 3 is extra. You can see here 1, 2, 3, 4, 5, 6. This will getting 3, 4, 5, 6. 6 is extra here for this, and this is getting 6, 5, 11 for 15 extra. Okay, so this value of this resistor will change much. But the advantage is connections, relative connections are very easy because they are sitting close to each other, you are able to make here. But the value of these resistor will vary. Another, if we do like this, now you see the effect. Now this 1, 2, 3, 4, 5, 6. You see this now it is getting equal. Whatever your gradient is there, they are getting equally distributed in this. But then what is that disadvantage? That how you connect these two. You will need, because finally these you will have to connect here and here in one plane, and this also you will have to connect in another plane. You have to connect this to here in another. So the connections they become problematic, and there will be some parasitic because of these connections also they will affect. Okay, so this you have to keep in mind, like this one, if there is a gradient, this resistor, though you wanted R1 to be equal to R2, but here most of the gradient will, here it's more, Here it's less. It has taken all the gradient here, so this resistor will be different. Here the gradient is uniformly distributed because this will be R1 plus delta and this also will be R2 plus same delta. In this case, it is R1 plus delta and this is R2 plus some 3 delta. So this kind of differences will be there. But here connections are becoming more difficult. So you can see here you calculate 1, 2, 3, 4, 5, like 6 here, and this is 15 here, 6 and 15. You see here 1, 2, 3, 4, 5, 6. So you can see 1, 3, 4. This is 9, and then 6, 4, 10, 12. So 9 and 12. So that way you are able to see you are able to reduce the variations. Okay, so there are many different techniques. So this is known as the interdigital. So sometimes you have to use an interdigital resistors. And another thing is, which is important, is you see here. You see there is something known as a neighborhood effect. You see this B is surrounded by two A's. This A is surrounded by two B. When you do the etching of in this area and this area will be uniform. So this means this width will be same. It will not be over etched, it will not be under etched. Right? But if you see this A, here it's an open. Okay, so since they're open, there can be more etching, over etching. So this width of this A will become less and this B also become less. So what we have to do? So we have to see that the surroundings are same. So I put another block here, which is a dummy. Okay, it is not adding here also, we have put dummy. So now this whole thing is completely matched with each other. So they have the same environment. This is known as a proximity effect, because here B is seeing here some structure uniform, but this A on one end it's seeing B, on other end there's nothing. So I have to put a dummy here. So there, because of then all these resistor segments, they are seeing the same environment. So that is important. In any layout, axis of symmetry is important. Axis of symmetry can be in X and Y. So it should be symmetrical. You can see here, you can place this AB in different ways. Like these two resistors are there, A and B, which are equal. I can place it like this. So now it's a symmetrical layout across this axis. Right? So this X and Y both are symmetrical. Now you see if the variation here, again it's a linear variation, 1, 2, 3 and 4. So what will the variation in A? 1 and 4 is 5 and 2 and 3 is 5. So both will vary same. So value of both A and B will be same if they are symmetric. This is interdigital. AB. Here it will not be same. You can see 1, 2 and 3. 3 and 1, 4. 1 is 4 and 1 is 6. But it has some, you can see axis of symmetry is different here. So variation is not same. This is again, it's symmetric. So but here value of A resistance is twice the big than B. Now there so there is something known as these resistors where you do the axis of symmetry, that layout is known as a common centroid layout. So there are 4 rules of doing a common centroid. One is their coincidence. This means the centroids of the matched devices should coincide at least approximately. So coincide means like this one. Here the coincide of B and A, they are both matching. You see the axis of symmetry of B is also this line, of A is also this line. It is matching in X and it is matching in B also. But here it is not matching. Axis of symmetry of A is this, axis of symmetry of B is this. So they are not matching. They are not coming on the same line. Okay, so this is axis of, so the symmetry should match, the coincidence should be coincide, and then their dispersion and compactness. One is dispersion. Like here, dispersion is not there. You can see BB are close to A. A is dispersed, but B is there very close. This is dispersed. Okay, they should be spread out. And another is it should be compact. Layout has to be very compact. Normally a squarish. You will not go for aspect ratio should be 1:1. That so ideally should be square. You have to try for this. So this is a common centroid layout. You can see if A and 2, there are two resistors, both value of same. You can place like this: A here, B here, rather than placing A here and B here. You have to place this way. So this is better. Okay, now if you again you can make more fingers. Then you can place like this. You have put A here and A here, BB here and BB here. So you can see here common centroid is matching. Dispersion is also there. It is dispersed, and so gradient is also spread across all these segments. So sometimes you have to use a shield. So this is a shield, is very clear. A you have put a shield, and this shield has to be connected to a particular voltage. So this is used in RF designs. Then you see in a circuit there may be some device which is consumes lot of power. So this is a power device. Now the thermal contours, this device is generating power. So these are square, these circles you are seeing, these are the thermal contours. Now if A and B resistors, alignment is also important. You are placing A and B like this, and you are placing A and B like this. So are they both equivalent, or which one is better? So you see here, the B is seeing this thermal contour, means this circle, all points on this circle will be at one temperature, all points on this circle will be at different temperature. So B will be at one temperature, A will be at another temperature, and resistance varies with temperature. Okay, so the value of A and B will vary, though you wanted the same value for A and B, but because of temperature, the value is varying. But if you align like this, then both A and B variation will be same. Okay, so this is not correct, and this is the correct way of doing a layout. Now both integrated and common centroid also you can use. So you can see this. You can spread out between this. D is a dummy. So outer ring is all dummy, and you can see how 4 segments, 16, how you are spreading out A and B. So when the segments are more, the layout is also becoming more and more complex. Now this is a differential pair. So you can have like this AA, BB, AA, BB, or A, BB, A, like this. So these are the various process variation can be averaged. It is a good matching. You can split them in various fingers. Okay, so you can see yourself now on an XY we have separated D and B here, D and B here. This is D and A, like this, and or we have made like axis of symmetry common here. So again, you have to put these dummy devices. These dummy transistors are put for a proximity effect, and these dummy transistors, they are not connected to any voltages. They are just dumbing. They will be floating, whereas these are the real transistors. So these are the dummy ones. So now if you see, if you are giving this is a transistor, you are connecting some voltage here. So why this is wrong, why this is correct? Because if your voltage here is 1, this is a metal line, but metal will have some resistance. So this part will, if this is 1, this will get 1, but this will not get 1. There will be some drop across this. Okay, so this drop will be more here. But if you connect 1 here, this segment and this segment will have the same drop. So this is matched. You can see axis of symmetry is there. This This is excess of symmetry. Here there is no excess of symmetry. So excess of symmetry is very important in these. So matching may occur because of these oxide damage, impurities, bias, temperature, etching. All these things can happen. And it may, the absolute value of any component may vary. So you have to match these components to nullify the effect. So these are some of the techniques. Use transistors with the same orientation. So minimize the contact area by stacking transistors. It has to be symmetric and shielded guard rings, and these are the common things you have to do. You should always have a multi-finger transistor. You should never have like this is a multi-finger transistors. So in a multi-finger transistor, the rule is the width of each finger, gate resistance of the finger is less than 1 by GM. So based on this, for low application, 1 by 10 is fine. So this is a thumb rule by you have to generate of this multi-finger capacitance you can calculate. And if this is W by 5, so this is a formula you can calculate. So in a multi-finger, you can optimize the number of fingers so that the parasitics are minimized. So you can see this is a differential pair. You can like this, or like this. Okay, so now the way asymmetries may lead to mismatch, introducing input referred offsets. And if you have to suppress these noise and non-linearities, so C and D you can see here, this is a symmetric layout. This is not a symmetric layout. This also is a symmetric layout. So it will even out the noise and non-linearities. Now there is a effect of a gate shadowing. Now if you do this source drain implant, you see the source drain implant is a tilted implant. This is normally tilted by around 5 to 8, 9 degrees because of channeling effects. But tilted implant has disadvantage because of shadowing. You see this region here, you will not get any implant. That is the shadowing. So there will be some asymmetry in this region. Okay, so then you have to layout in a correspond like this. If you do a layout like this, so here the asymmetry will be in both the drain and source, whereas in this case the asymmetry is towards this region only and not towards this region. So here you have made both drain and source symmetric. So that is the advantage. So you can see the asymmetry can be emulated by adding dummy, and you are putting some dummy transistors also here. So this is a common centroid configuration. This is a common centroid. As I told you, if there is a gradient, so if you place the transistor in this, the gradient will be divided across these transistors. And cross coupling. Now when you connect the transistor, there will be some cross coupling effects. Like this transistor you have to connect with this you have to connect with this, so you can calculate these cross coupling effects. But this approach, you are able to filter the gradients, but some other effects are added. But overall it gives you a proper matching rather than putting in all the fingers close to each other. Now there are certain shallow trench isolation rules also, because nowadays these transistors, they are separated not by a field oxide, but there is a shallow trench isolation, and so you have to insert dummy fingers, because otherwise there will be a trench across these. So you have to like these two, we have to there is one gate, we are putting a dummy gate here, and this gate is grounded, as you can see here. Okay, it is like this. So this is a properly, it has been done like this. So this also you are putting a dummy here and here also. So similarly with the well proximity effect. So this your implant, they are getting scattered here. So that will also affect at this particular border. So again you have to put a dummy here to alleviate this problem. So all these then interconnect capacitance, these fringe capacitances will come, and you have to see, you have to adjust these capacitances. Then there's a latch up issue because BJT is formed at one end, and you have to suppress that BJT. What you have to do, you see, if you can, there is a CMOS structure, NMOS, PMOS, and Q2 and Q1. These two transistors BJT are found. They are interconnected in such a manner. If this transistor is on, what happens is you raise slight a small voltage here at X point. What happens is IB will increase, this transistor will become on. So it will start drawing current here. Alright, so IC will, if there is a small IB, huge IC will come. And some of this IC will go in as an IB of this. It will turn on this. So this IB, huge IC will come here. And this IC, some of this IC will go in this IB also. It will further increase this IB. This IB increases, IC will increase beta times IB. So you can see here, then a stage comes, a lot of current flows from VDD to ground. So that is a latch up. So for this, you have to minimize this R2 and R1, because if the node potential at node becomes 200 or 150 millivolt, V base to emitter voltage should be 250 millivolt. Immediately this Q2 will on. Similarly, this voltage, this is a PNP. So this voltage, your emitter to base voltage should be more than 200. So how you can reduce this voltage? By reducing this resistance. So this contact R2 and R1, substrate and well contact, you have to reduce. You can eliminate normally if your gate is long, connected to metal, long metal, then metal act as an antenna. And while doing CMP and etching is a dry etching, dry reactive ion, it's a reactive ion etching, so it can destroy the gate. So what you have to do is you have to cut this metal short. There is a rule, you cannot have this metal more than a particular limit. So you are cutting this metal here and splitting between M1 and M2. You can see here M1 and M2. So these, then you have to, the sensitive circuits has to be surrounded by guard rings, as it is seen here. Guard rings needs to be connected to different voltages. Okay, so these are some of the guidelines for noise minimization. You have to maximize separation between digital and analog bias lines to be separate. Guard rings for isolation. Multiple supply pins you choose. You choose wells for isolation, shielding. Use bypass capacitors. Use metal lines with constant bias and things like that. So all these things you have to, and various blocks you have to place. If LNA is a very sensitive block, DA and is a very sensitive, is a very high speed block, these two blocks should be further apart from each other. Don't put these two blocks close to each other. So in a layout where the circuit is complex, how to place these components, which is known as a floor plan, that also is very important. That will decides the overall behavior of the circuit. Now I will show you some of these layouts which we have done, taking care all these things. You can see some of these layout. This is a 24-bit ADC, this particular thing. So it's a 24-bit sigma delta ADC. So you can see here, this is the digital part, or I will try to, what is ready, increase the size so that you are able to, I think now it should be clear. So it's a 24-bit sigma delta. Now this is the digital portion, and this is the capacitor array. This greenish, this is a bypass capacitor. There is one LDO also. This is one LDO voltage regulator. So this is a bypass capacitor green, and this is it's a two-stage modulator. This is the first stage. This is second stage. This is voltage references. These are the capacitor arrays. So there are around 128 bank of capacitors. So this violet color, and these are the pads. So this whole thing is this dimension is 2 mm only, and by 2 mm. So this is how it looks. Some of these layouts, and these are a different. Now I will show you this. So this is again, it's a voltage regulator, and this is a power MOS. It gives 150 milliampere of current. This one, and so it's a one transistor but multiple fingers. There are many fingers, so that it is able to give 150 milliampere of current. So this is again, this is a single power MOS which can give 3 ampere. You can see that there are multiple fingers, and the challenge is to lay out these fingers so that all fingers, they should conduct same current, because if one finger or few fingers connect more current, then they will finally burn out. So current has to be divided equally amongst all fingers. So similarly, this is an LVS driver. It's a quad. There is a 4. If I increase this, so there are 4 segment, 4 quad, 4 like 4 LVDs are put in one chip. This is 1, this is 2, this is 3, this is 4. So you are seeing more or less it is symmetric, and all these 4 LVDs are put so that there is no interference between amongst these 4 blocks between them. So this is your 485. This is your 488. This is a transceiver. This is how it looks. This is 422. So this is a C2V. So this is the digital part, and this bluish is again a capacitor array. You can see this is the power ring for a digital part. This thing is a power supplies, power and ground for digital, and this is a power and supply for analog. So you can clearly see how they are separated. And power grid, VDD and VSS for analog, and for a digital they are separated. Areas are also separated so that they should not interfere with each other. So these is a clock high voltage drivers, and you can also see here these are various op-amps here put, and drivers, which is the last stage. Here criticality is they have to drive the very high load 30,000 puff, and the speed should be 10 megahertz, and the voltage levels are also very high. You can see -5 to 3 volt input and 5 volt to 15 volt output level. So switches are also high. They should be able to drive high currents. So these are some of the. This is again a power MOS. This is a single transistor. It can give 3 ampere. So there are many fingers in this. 15 points. They are distributed for current monitoring, and the temperature. There are in this device. There are 15 temperature sensors, because which are set up across various points in this circuit, so that the temperature of each area is monitored, and where the temperature is shooting up, you have to take preventive measures for that, so that the device doesn't burn. So these are some different types of inductors which we have been made in different shapes. So these inductors are made by metal, some polygonal, some squarish, and different shapes. These things have been made. This is one. In fact, this is one circuit which is an APS, active pixel sensor, which is a camera, basically CMOS camera. So this array which is not shown here, it is this. This is a photodiode here. It's a PN, and there are 320 DACs, ADCs, which are placed here. The 12-bit ADCs. and dual slope these all. So total, because this dimension is 320, this dimension it's an array of 256 cross 320, so 320 DACs have been ADCs have been put here. So this placement is very important in a circuit. So this is a 16, this is a controller, it has a 16-bit microprocessor in this, and this also is a controller which has a 16-bit microprocessor, and it is a radiation hardened. And this is a baseband, this is a GPS receiver, which is an GPS receiver. It has a 32-bit processor, Leon processor. So the chip area, as you can see here, is 11 mm by 11 mm. It has 4 million gate, 4 million gate into, you can multiply by 4, so 16 million transistors this particular is having. It has the 32-bit processor, and there are several peripherals and some memories are also there in this. And so these are some of the designs which academic institutions we have fabricated. They have designed NIT, IASC Bangalore, IIT Kharagpur, then Nirma University. So some of these designs we have fabricated for them. This I'm showing you some of those designs. These So as an overview, let's go to the previous. So I've shown you some of these. Some of these designs. So now we have covered starting from the design. So we have to do the front end part. We have to finalize the architecture, and then do front end simulations. And if the specifications are met, then we have to go for a layout. We have to do the layout, then do the PEX part. And if the PEX is also meeting the specification, then we have to do the complete taking into consideration the RLC part. We have to do the complete simulate the circuit for various parameters, and then we have to release GDS. If it doesn't work, then you have to change either the layout or you change your architecture, so that this particular thing is able to work. So this is the complete flow for an analog. And as I told you, in an analog there are various modules, and if you have to learn this complete analog design, so the starting point is very the various blocks I had shown here. So you have to take up each block by block, and you have to go through it, solving their these. So this, like common source, which is a voltage to current conversion, then common drain, voltage to current, simplest voltage follower, common gate, and basically all these controlled sources. So current controlled common source, and common drain, common gate, then diode connect transfer, active load, then a cascade, then a folded cascade. Then comes your differential amplifier, then cascaded differential amplifier, then current mirrors, how to make current mirrors, and then your how to make a cascade current mirror, what is the advantage of a cascade, how to increase the output, how to make high output impedance, how to do matching, how to do current multiplication. So these things one by one you have to take up, and you have to understand the what is the large signal model, what is the small signal, how to derive parameters, various parameters, like your dynamic range, your output swings, your frequency response, your poles and zeros, and biases, how to noise, how to connect the noise, and from the front end part, and after doing the layout, the simulation part. So then only you will be able to realize these circuits. And basic building block is an op-amp, and once you are able to do the op-amp, and you see another thing is here there is something, and whenever you start design, there is something known as a design kit, process design kit. I will there are some 10-15 minutes I will cover. So what is the meaning of a process design kit? So process design kit is a collection of files which will help you the custom, which will help the circuit designer to be able to design circuit. So what these design kit includes? These design kit includes what are the components, active and passive, what are their names, what are their symbols, what are the models, and how to make the layout for these, and what are the design rules, what is the LVS, what are the technology files, what is the parasitic for each layer, how to extract, and scripts. So all these data they are included. So normally the foundries, fabrication, manufacturing plants like TSMC or UMC, so these foundries they prepare this PDK and they give to the design houses, and design houses uses this PDK to design their circuits. And so PDKs are made for the designers. It has PDK specific for an even a design flow on a particular design tool, like whether you are using a Synopsys or a Cadence. So your technology files have to be compatible with those design tools. And now, since the transistor sizes are falling, and when the your mismatch becomes more, on-chip variation also increases, and with this the yield suffers. And nowadays people talk about design for manufacturability, design for yield. So what are those issues? Though some of those issues are also highlighted in these PDKs, how to enhance the yield. So I will give you one example. You see, this is a band gap circuit, band gap reference. It's a voltage reference. This is a schematic. Okay, so what the PDK will do is, like, in this is a circuit. So you should be able to simulate this circuit. Now you have simulated and you have seen this references, how much variation per temperature it is coming. And based on the P cells, now this is a transistor, this is a transistor, this is some resistor. So based, this transistor finally has to be laid out. So you call the P cell, and P cell will lay out this particular transistor, and you call this element for P cell. For this element, they will do all these layers for this, like as shown in this figure, and it will interconnect. So you get a complete physical design of this, and you can simulate this physical design to make. After now, this simulation will takes into care of parasitic elements also, whereas if you simulate using this circuit, it doesn't take into care the physical part. So all these things are possible by using an integrated analog design flow. So technology file means what are the different layers, what are their names, how many vias, how many metals, what is the stream in, what is, because in a layout normally each layer is represented by a color. So what is that color for each layout? So those things are there. And P cell is known as a primitive, it's a parameterized cell. It will have the information about the symbols, it will have a CDF, and it will have entire information about the length, width, electrical information like what is the capacitance, what is the resistance, and some logical information, terminals, how to connect the terminals for a transistor, also for an active component also, and for a passive component also. Because to aid the designer, otherwise the designer has to lay out all those layers himself. And if he calls, like for a transistor, so you have to make a transistor of 4 by 1 W by L, then you call this P cell for that particular transistor, it will place those layers automatically. And contacts, it will give you the contacts there on the transistor, and you can interconnect those contacts. So these P cell library use, it has all device characteristics. Device characteristics means about the geometry of the device, about the voltage behavior, about the spice netlist. All information of the device is there in the P cell, and so this way it helps you. So this is a symbol of a transistor. So you will have these CDS term D, G, S, and there will be some parameters here. So this is how it is represented, and a layout parametric scale will, like you can see this, all various layer, various instances they are put. It will give you a layout of a transistor like this, where it is showing two contacts here, 1 and 2 here. So all these layers are active area, your diffusion, your poly, your contact, your metal, your via, it will be there in this. And it can calculate the when you connect the parasitics, when you connect the two transistor, you have to calculate the parasitic of the interconnect and take into consideration. So that is a schematic driven layout, where from the flow you have made a circuit, and your schematic is formed based on the your layout is formed based on the schematic. So your circuit drives the schematic. So schematic driven layout, you have design specification, you have made the circuit, and finally you have simulated it, and after simulation you find it is meeting the specification, and then you can finally have a schematic driven layout. So it will use the P cell, it will make the complete layout and give it to you. You have to interconnect various elements, extract the parameter, resimulate, and then do the post layout simulation as shown here. And then finally, so this is the a summary of the design development kit. So these are the layers like of a particular UMC fab, UMC foundry, like WP means P well, N well. This is layer number. This is the abbreviation. GC means gate contact. This is active. This XP means P diffusion, N diffusion. CS means contact. This is a gate poly. M1 is metal. This is the number, and the color is also there, which is not shown here. V2 is second via, M2 is second layer. These are the layers. So you can see here, for an analog design, what you need is, you need a model file. Model file is a spice parameter. You need a P cell, which is gives you all the layer information for placement, and you need some IO libraries and the technology files like this files. What are the various layers? You can design the circuit. And for a digital, you need the lookup table and the Verilog models for making, and the technology file for doing the synthesis and doing the APR. You need a standard cell library, where like in UMC at more than 560 standard cells. So these standard cells, Verilog models will be used to synthesize the circuit, and they will give a complete form, and then TLU, this is a lookup table, will be used to evaluate the parasitic. Then IO for IO pads, and finally you can close this. So this is how, in a brief, today we discussed the front end part, how to make the, how to realize a circuit, how to do the biasing, how to adjust W and L, and we discuss some of the issues pertaining to the layout. In the next, we will take one example. We will take an A to D converter, how to design an A to D converter, and what are the various steps, what are the issues. So the next lecture will be on A to D, which will be held tomorrow. And now, if there are any questions on whatever we have covered today, you can please ask.
Any query from any of the nodal center?
Thank you so much, sir. Now we'll start with our next session at exactly 2:30 p.m. after lunch break.
Just a limit. हार्मन कार्डन स्पीकर है ना ये हार्मन कार्डन इसका स्टार्टिंग प्राइस इज 45,000 Naveen sir. Naveen sir. Naveen sir. चलो पकड़ ले यार.
Water. They're asking for water, no? Yeah. So, hey, how about this? Hey. जी यहाँ पर यहाँ आते हैं otherwise you can take this ये भी शुद्ध है Yes. Now let's proceed with our next technical session that is based on analog design simulation. For this, I would like to introduce Engineer Deep Sehgal from SCL Mohali. Engineer Deep Sehgal is working as scientist in VLSI design in Semiconductor Lab Department of Space, Government of India. He is graduated from NIT Surat, Gujarat in 1996 in electronics stream. He joined SCL in the year 1998 as VLSI design engineer. During his more than 17 years of experience in design, he has worked upon many projects in various domains on 3 micrometer to 0.18 micrometer of technology nodes. His first major work was in biomedical field for the design of ultra-low power pacemaker chip,
I will change the slides.
wherein he designed 0.7 microampere bias current op-amps, switched capacitor-based full-wave rectifiers, switched capacitor-based voltage-controlled oscillators, and telemetry transceivers. He has been involved in multidisciplinary projects for the development of infrared camera system for night vision applications. Here, he was to develop a readout integrated circuit for infrared detectors with operation of chip at liquid nitrogen at a temperature of 77 Kelvin. His recent work has been in the field of power management related to linear voltage regulators with overcurrent, overtemperature hysteresis protection designed and fully tested on silicon. CMOS-based imaging test chip with verification done on first
Is
silicon
it being
with
broadcast now?
successful capturing of photographs of objects and human
और लोग
faces.
तो नहीं देख रहे ना अभी.
His dominant field of interest has been in the area of analog design. In all these years apart from design work at levels of project member to project lead, he has been into critical and peer review of many designs, has been in the project review committee, has delivered lectures in department, workshops, conferences, and has been involved in testing and debugging of fabricated designs. With these few words, I would like to invite Engineer Deep Sehgal to please start the session on the topic of analog design simulation.
Thank you. बैठ सकते हैं.
Yes.
Good afternoon to everybody. The topic which is there is analog CMOS design and simulations. And this topic is quite broad, but the way I will be covering this topic is basically it is split into two parts. One is the analog designs and other is the analog simulations, which are the inherent part of the analog CMOS design process. Let me start with the little bit of history of the microelectronics. As you are seeing on the slide, we start from the year 1947, which is also the day of the year of independence of our country. You can see that worldwide in 1947 BJP transistor was being developed. 1957 integrated circuit came into the life. 1960s the first TTL family, 1970s MOS processor, and then CMOS. And then a curious phenomena happened in the year 1980, which was that many experts of the industry, this is audible to all.
Yes.
The experts of the industry were predicting the death of the analog circuits. And the reason they were giving for the death of the analog circuits was because by the time of 1980s the digital circuits were proliferated almost in the every area of our gadgets, our microelectronics devices, and more was being seen as the proliferation of the digital circuits. So but let me reiterate that we are in the year 2017, and not only CMOS is still continuing, but the analog circuits are also still continuing. So we will come back on this topic, that what has given the fuel to continue the analog fuel to the analog circuits. One more family, one more thing which is very interested in the microelectronic circuits is that if you see over the years of 50, it is almost more than 50 years, and there seems to be not only no end to the CMOS circuits, but also this industry has grown exponentially for the 50 years, which is quite a big time for any industry to sustain the exponential growth. Not only this, even if you see the steel industry, even if you see the plastic industry, no industry could endure the exponential growth for the 50 years. It's a very interesting thing for the microelectronic circuits, which took birth somewhere in 1950s. Now, coming to the design or the analysis. Now, how do the young engineers see the design? How do young engineers see the analysis? The major difference is this only. When you do the analysis, you have a one circuit, and you are deriving the properties of that circuit. And when you are in the design process, you are given the reverse of the problem which we were often leaving to our semester exams, the end problems of our chapters. And there they always give you the reverse problem, that is the properties are given and you come up with the circuit. And now the novelty, now the your creativity comes into account, and the same properties, many circuits can be developed. And that gives design as a not only a very interesting field, very challenging field, but also your all creativity comes into account. Now, what is integrated design and what is discrete design? If you see how integrated analog design differs from the discrete one, uh, I think in the college levels we all are doing some work on the substrates, some work on the breadboard, some work on the devices. But have we grasped that integrated analog design is in some way different from the discrete designs? The 4 points which I have listed here are, what I mean to say is that substrate is same for the integrated analog designs. Now the designs are integrated. Designs are on the one substrate. Many components are on the one substrate, and you have to deal with this problem. In fact, the cramming of the many components in the one chip gives a plethora of problems. Not only that, the geometry of the active and passive devices are at your hand now. If you go to market, you purchase a resistor. If you go to your engineering college lab, you purchase a resistor, or you take a resistor, capacitor, inductor. You are having the fixed components given to you. But here in the integrated circuit design, you have the ability to tune up your active and passive devices. That is the geometry of those circuits. Now you are on the simulation lines, not on the breadboard lines, and you are also limited by technology to only few components which you can maybe use, or based on these 5 or 6 variety of components, you have to actually carry out the digital analog design, the CMOS analog design. Now coming to basics, what is analog and what is digital? This is a very tricky question. If you see, somebody can argue that no signal is digital. In a way is right, because any signal, when it goes from one level to other level, either it has the finite jump time, finite rise time, or the finite fall time. Now the only thing in the digital is we are ignoring these times, and we are only capturing the levels which are high or which are low. But yes, any signal in the last analysis is analog in nature. But what distinguishes the analog and the digital when we talk of that? You see this table here, it says that if the amplitude is continuous and if the time is continuous, you have the signal which is analog. And if both are discrete, you have the signal which is digital. But often we do not talk of this, the third category of the signals, where the amplitude is continuous and the time is discrete. What does it mean? That let me have a sine wave. I will take the samples of this sine wave, and I will only be interested in those samples. But there is no guarantee that these samples cannot have any magnitude. So the magnitude wise, the signal appears as a continuous. It can take any resolute value, but time wise it has been discretized, or rather I have to say I am not interested in the intermediate samples or what is happening between the sampling time. So I come to the other category of signals, which is sampled data analog signals. The time is sampled, but the magnitude is not sampled. On the second row, time was also sampled, magnitude was also sampled. Discrete means I have sampled the things. I have quantized the things. I have the finite number of things. Continuous means I have infinite number of things. I cannot predict whether the analog will be, magnitude will be 1.1, 1.001, whatever level you want to take it to. This is pretty obvious. Analog design flow, it's quite a straightforward flow. Any design starts with the functionality, starts with the specifications. And also I have not written here, but any design is oriented towards some application. So remember these three words. Any design is definitely for some functionality, for some parameters or specifications, and for some application. You cannot design an amplifier if you are not knowing what is your load going to be. You cannot design an engine if you do not know how many persons will be sitting in the car. So we can talk of a generic designs, but generic designs are not they're rather very less in the number. More of the designs are oriented towards some particular task. Now the second process which comes is the design process and EDA description. Okay, you take the entry of the design in the schematics. Then you carry out the third step, simulations, and then a major change comes. Till now you are in the electrical domain. Now on the fourth point you are entering in the physical implementations and verifications. That means you are converting your design from the electrical domain to the physical geometrical domain. And that means that you have to start seeing your design not only in the schematic way but also in the geometry of the layers. That is microelectronics. So it is the overlay of the geometry of the layers which ultimately gives which ultimately goes to fabrication house, a foundry, and the chip returns. So you are transferring your design, which you think is the basically a electrical schematic, into a layout, and then in turn which is created on the silicon. Now this process of physical implementation has introduced its own realities, which is parasitics. Now where you did not intend, resistor has come. Where you did not intend, capacitor has come. Parasitic is anything which is unwanted. Parasitic is anything which is unintended. So it is not your capacitor which you have placed on the design. It is the capacitors which has come because of the interconnects, which has come because of the geometries. Now you have to take care of those parasitics. So what you do, you carry out the parasitic extraction, take it back to the simulations. Again, this loop may continue for a long time. Once you come out from this loop, after parasitic extraction, you go into the design release to fabrication. So this is a very generic analog design flow, and the tools. I think I have a slide on the tools. Yeah, I will go first on this slide. This is the industry analog simulators. These are the very famous simulators which industry is using. SPICE stands for Simulation Program with Integrated Circuit Emphasis, developed in the University of Berkeley long back. And now it has been taken by the Synopsys as the EDA vendor. You have Mentor Graphics, Eldo, and you have Cadence, Spectre, and XPS, FastSpice. And now I will come to this FastSpice in the coming slides. You take, you see, you may raise a question. What are the advantages of the simulation? And the points are written. You can read those points. You have eliminated the breadboards. Now you have got the capability to monitor the signal at any point in the circuit. You cannot do it on the PCBs. You cannot do it on the breadboards. Your access points are limited. You have only the outer periphery of the chip. Now where you have to debug, you have to put the CRO probes, multimeters, any instrument. But once you are in the virtual environment, which is the computer environment, almost all the nodes are accessible. Rather, all the nodes are accessible to you of your circuit. So debuggability analysis becomes easy. Now the third point is you have the ability to open the feedback loop. What does it mean? See, feedback is a concept which has given birth to many novel circuits. And as an analog designer, I will give you a feedback that if you really want to grow in the analog field, you have to understand feedback from the very basic principles. Feedback is a very generic concept. It was not Harold Black who came up with this idea, was not the physicist. He was even not the he was not the professor at the first. He was actually working as an engineer in one radio electronics company. And the problem was that the amplifier gain was changing. It was changing with the temperature, it was changing with the parameters, and there was no control on the amplifier gains. And one day while he was on the ferry, he was writing on the newspaper, and he came up with this concept of feedback. Later he showed that newspaper to the patent agency, and the patent agency did not approve this idea. The reason was that feedback is going to reduce the gain. Now when I have made this statement that feedback reduces the gain, please see that it is the negative feedback which reduces the gain. It is not the positive feedback. So Black was talking of negative feedback, reducing the gain, and this was a very it was seen as a negative thing, a discouraging thing for the electronic circuits. But the power of the feedback was, although it was reducing the gain, but it was stabilizing the gain. Stabilizing it with respect to temperatures, stabilizing it with respect to load conditions, stabilizing it with respect to process changes, stabilizing it with many changes. So this was a powerful, ultra powerful concept on which PLL stands, on which voltage regulators stands, on which the sigma delta ADC stands, and on which all novel circuit stands. So my message is that please see this feedback. Don't assume that you know the feedback. See it from all angles, control theory angles, your own circuit analysis, and start using it in your day-to-day design and analysis things. In the simulations, you can easily modify your circuit. Not so easy on the breadboard. Anybody who has done the work on the PCB, he knows how difficult it is to modify a breadboard or a PCB. Now you can analyze the circuit at various temperatures very quickly and various process very quickly. The last line, at various process, means you should stop thinking your circuit as a one-time thing. Now when we design the circuit, there is a philosophy or there is a psychology that we take our circuits as something we have done, and we try to protect our circuits. Rather, we pamper our circuits. Why? Okay, it may be related to psychology, but the experts of the industry says that throw your circuit to all brutalities. Throw your circuit to all temperature corners, to all process corners. Process corners means manufacturing conditions are never the same for all the chips. Manufacturing conditions vary from one wafer to other wafer, from one fab to other fab, from one die to other die, even inside the die. Now, if you think that today I have designed something with the current of 10 microamps, with the current of 100 microamps, who has said to you that this current will remain same? It will not be same, and that analysis, if you do not do, assume that out of 100, maybe only 1 or 2 chips are going to survive. So it is a very important analysis which you can easily do in the simulations. But there are disadvantages also of the simulations. What are the disadvantages? It is very difficult to say the disadvantages of the computer world. But let me take the last point first. Computer substitutes your thinking. It does not happen in one day, but slowly it comes upon you. You start taking the numbers which the computer is performing, which the simulator is performing, and you start taking it so seriously that you are damn sure that these numbers are numbers only, and these numbers have meaning only. But you read now the 3 points on the top. Ultimately, it's a virtual world. Anything you are doing in the virtual world is dependent on the models which are provided to you. What are these models? These are the fabrication house as if put on your computer. It is the foundry which you have no access put to you. You go to any worldwide famous foundries, Samsung Foundry, TSMC Foundries, Tower Jazz, they will give you their PDKs, process design kits. In the process design kits, there will be models. Now you have to assume that this is the condition of the fab going to be. But condition of the fab only is as much accurate as your model is accurate. Industry has strived, industry has done much to improve the models, and today they are even using BSIM 6, BSIM 3v3, BSIM 4, and we at SCL is using BSIM 3v3, which is level 49 of the SPICE, that is HSPICE. Now there is a possibility that your simulations may not converge even. If you have a very complex circuit, it may happen. And time required, what do you think? The time required for simulations will be far more than if had you been working on the PCB or had you been working on the breadboards. Even for a very big chip, it may be months. So when I talked of fast SPICE simulator, fast SPICE is just that, to kill this time required for the simulations of, let us say, 10 million transistors, 4 million transistor chip. You require fast SPICE simulators which are not accurate, which have sacrificed the accuracy at the cost of speed. They are very speedy simulators. Now, anybody can raise a question. How do you design multi-million processor, multi-million transistor processors or memories? So you see now the power of the simulations, power of the computer world is now slowly coming into the picture. But there are other philosophies also. For example, abstraction plays the role. Anybody who is designing the digital circuit there, he will be knowing that they do not start from the transistor level, they start from the standard, they start from the standard cell library level. So what has happened that instead of starting from the transistor, they have moved one step up to the gate level. They model the gate with respect to timing, with respect to power, with respect to noise, that is noise margins, and with respect to one more thing, that is the signal. Maybe it can be even the short circuit currents or the power divided into intrinsic and extrinsic powers, whatever. But the gate library, standard cell library, is the thing from where they start. So they have moved one step up. When they design very big circuits, they even start modeling the bigger blocks. In this way, they kill the complexity. So it is the divide and conquer approach. The other thing is, signal type of digital circuits leads to simplification. As I said in the beginning, although no real life signal is digital in nature, you make it digital in nature or you interpret it like digital. But in the digital circuits, we are only ultimately interested in 1 or 0, which is the some higher band of voltages and the lower band of voltages. This is your simulation environment. And when you are using the simulator, be careful. All the arrows and the words written there, you are playing with actually. In the left side, you supply the netlist, which is your nothing but the circuit representation written in words or in schematics to your simulator. You also give your stimulus. Stimulus is something which you are giving at the test vector to check your circuit. Now, the third is you are providing the models to your simulator. Now, as I said in the some slides early, that these models accuracy is ultimately going to produce the output accuracy. Your stimulus, the nature of your stimulus is going to decide what simulator is going to do. Now, if your stimulus is wrong, if your models are wrong, don't expect that simulator numbers will be right. Neither, at the same time, you have to be very minute, you have to be very detailed on the numbers which the simulator is producing. Experience wise, I am saying just take that numbers and be ready to give some plus minus 20%, plus minus 10% to those numbers, and only interpret your results in that light. Because on the fab side, when the chips will be coming out from the fab, there will be a lot of variation on the chips, on your results. So if you want to design, for example, 85 megahertz processor, then the best way is that give it to the worst conditions and design. Although it is a pessimistic approach, but give it to worst conditions and design. Worst conditions means lowest voltages, highest temperatures, slowest process corners. If the design is passing that point, that means almost all the chips at least will be giving greater than 85 megahertz. This assumed that your models are right. Take care of your operating conditions. Just now I said that okay, in SCL we have a 180 nanometer technology. So we are having two types of transistors. One is the 1.8 volt transistor, other is 3.3 volt transistor. Now when the voltage numbers which I have said to you, they are basically typical in nature. 1.8 doesn't mean 1.8 only, it is plus minus 10%. So it can go from 1.62 to 1.98. 3.3 can go from 3 to 3.6. What does it mean is that your operating voltages are going to change. And you have to take care of your typical voltages with the plus minus 10% variations. Now what do you think of temperatures? In the college life, even if we simulate 27 degrees centigrade, we feel happy. But as I told you, don't pamper your designs. Forget, give your design to all the worst conditions, and it has to pass. Then only that design is called robust design. Now in the space environment, where they because our lab comes under the space environment, they always simulate the circuits from minus 55 to minus 120 plus 125 degrees centigrade, or at least minus 40 to plus 125 degrees centigrade. So design becomes tougher. The thing which is working at 27, you have to fine tune it further to produce it working even at minus 40 or at 125. So your temperature regime is quite big, your voltage regime is quite big. Then you have a multiple process corners. And I will come on the next slides. What are the other operating conditions which can come upon your design? Now see the arrow below, options. See what happens when you purchase a tool. The tool vendors set a default options for your tool. We often live with those options. We never play with those options. We take it like that as if they have given us the best options, but sometimes not. For example, if I have to design a pacemaker chip, pacemaker stands for the implantable heart performing device. Now its battery life is important, and this battery may has to work for the 10 years because daily it will not be implanted. So you can understand that how low current or low power this chip is going to be. And the op-amps which will be present in this chip will be working in the regions of nanoamps, or at the most some 1 or 2 microamps, at least below 10 microamps. If you are dealing with such type of bias currents of your op-amps or bias currents of your analog block, be ready to set your options to the low current levels, because the options which are set there, they cannot have this much of accuracies. So what is the point of simulating a circuit when the option is not set for the microamps and you are simulating a circuit in the nanoamps? So, and you are not aware of that. So ultimately all the numbers which you are seeing is junk, and circuit will not perform like that. Later on, at the end of the day, when you will debug the things, you will come to know that options were not set in that way. But it is a costly process because chip is out from the foundry and you have now to reproduce it or rerun it. It's a costly, it's a time-taking process. Okay, what are the analog simulator features? This I have just listed down. I will quickly go through it. You all know that the analysis which we perform there, and there are many more analyses which we can perform. In the similar way, what are the elements which are supported by the HSPICE? I have just written from the HSPICE manual, but I will give you one important point, not this slide, but the point is that please read your manual of your software very carefully. There are two approaches. One is when you purchase a software, or when your college is having a software, or your institute is having a software, we can always call the application engineers of the EDA vendor companies, and they can give you a good training. Rather, they try to give you a good training. but still there remain certain areas which unknowingly that application engineer could not touch on that day. Now, if you do not have the habit of passing through the manual, I think it will be difficult for you to be a real master of your software. This is also another important area which the designer has to deal with. Either he makes his training very powerful, or let him absorb all the details of the software nicely. By the details, I do not mean just the menus and just the drop down or the pull up menus, but the what is happening inside the software, which manual does throw some light upon. And okay, these are the advanced features which are there. I don't know, but these features are really to be explored, because I come from the analog field. I'm not from digital, but in the analog, I have found them extremely helpful. Extremely helpful. You see the third feature, which is Monte Carlo. Now, Monte Carlo is a feature which can take care of all your problems of voltage variations, all your problems of temperature variations, and all your problems of process variations. So PVT, the industry calls it process, voltage, and temperature variations. And the third side I will add, or the fourth pillar which I will add here is radiation. Now, radiation is not being talked of because we normally make the chips for the our commercial gadgets. But when imagine you have to make a chip for satellite. Now, if you have to make it, satellite will be subjected to huge radiations in the outer space, and ultimately they will disturb. Radiation can disturb, can kill your entire circuit. So the fourth element is the radiation. Monte Carlo can cover it very nicely, and it can give you an overall judgment of your circuit. Not at the typical corner, not at 27 degrees centigrade only, but how and what numbers, what sigmas, what averages you will be finding when this chip will ultimately run in the foundry. So start using the Monte Carlo analysis as the keystone of your all simulation environment. Then there are parametric sweeps, data driven analysis. This all you can go through in the any Aldo, Spectre, or HSPICE manuals. Okay, simulate with precaution. Still, why? You remember? Okay, I have come through this experience, and I have done the errors also. That you can interpret your data wrongly. That is one, and your data itself may be wrong. So what I want to say is, when you are simulating, be careful. It is always good to have some estimation of the number which you are going to have as the end result of your simulations. For example, you are simulating an op-amp, let us say, and you do not know how much gain is expected, at least some judgment of the gain. Then suppose your SPICE simulator is giving you 80 dB. You have no idea, is it really rightly coming or not? So that means what? That means that those hand analysis days are not over. That means that the paper and pencil approach can never be taken off from the real designers. That means your dependency on simulator should not be that strong that you have no indication of what frequencies, what UGVs, what gains, and this is more so towards the analog side. Digital domain people are even thinking of straight from RTL to silicon realization. They have so much done on their softwares, but analog design is still not nowhere close to that level. So paper pencil approach cannot be dropped. Okay. Now, in the beginning, I said to you that the industry experts predicted the death of analog, but it has still not happened even by the year 2017, while predicted in 1980s. Why? So these are the one of the major reasons which are propelling this analog design, and it will keep on propelling this analog design forever. So you see, till the microelectronics remain. Sensors interface. What does it mean? I was in one conference where one person from the Cadence was showing that almost, if I remember, 20 sensors are dealing in the mobile and in the modern gadgets. So huge are the sensors now. You see vibration sensors, you see accelerometers, you see even they are sensing the ambient light and adjusting the screen brightness. Even there are the sensors which can sense the temperature, which can sense relative humidity. So sensors are everywhere now. And the next world which the industry is talking is not smartphones, but they are going to be IoT devices, where sensors are almost all the corners. So these sensors are basically analog in nature. Someday you have to process this signal, you have to convert it into digital. Then only digital people come into play. So this field is in fact, instead of demising, this field is much increasing. The second area is high speed digital. Gigahertz digital signals are, there is a book which is the magic. I think it is by Paul Horowitz. It is a very famous book which deals with the high speed digital things. And high speed digital is a very tricky things. Reflections happen, signal integrity comes, bounces happens, power bounce, ground bounce, and these all makes your digital signal look like as if am I dealing with the analog signal. Ringings, so much of ringings are there on the digital signals. So it's very difficult to make gigahertz, hundreds of megahertz digital communication chips or even the digital processor chips. Now memory design. Memory design is on the borderlines. You can say that memory is digital in nature. Yes, it deals with logic 1 and logic 0, but memory design is quite analog. If you explore a DRAM chip, you will find SRAM chips, DRAM chips, many circuits which are basically designed in the analog fashion, later on passed to the memory groups. And you see the power delivery. Ultimately, you have to do the power, you have to feed the power to all the chips. And this power delivery system is basically analog in nature. Voltage regulators, LDOs, DC-DC converters, even boost converters. And nowadays, solar panels, the circuits behind the solar panels, they all are basically analog in nature. So there is a very interesting world. If you are really want to make your career in the VLSI design, then I will say that do think of those areas. Take one of your area, and there are very interesting circuits people are even today doing. And the wireless communication in the last, they are talking of even the 5G communications. So RF is a big world, and optical communications are even being talked of. So it is so don't see that there is because when we often talk of analog, we do not think anything beyond amplifiers, or we do not think anything beyond maybe filters or maybe ADCs. But that is only a very small part of the complete analog world. But then why analog design is that difficult? It is quite difficult. The reason is, one thing is, you talk to digital designer, he will mainly talk of speed, which is called performance, which is called delay, which is called by many other names. But he's talking of speed. He's also talking of the area of the chip, which is nowadays nothing, because the industry has gone even up to the 14 nanometers, and they are starting talking of 7 nanometer as the spot where they can live for many years. So area is no more a big thing in the matrix, but your speed and your power consumption of the chip is on the top. And apart from that, your signal integrity or your noise margins. So what I want to say is, the world of digital designer ultimately gets it's a limited world. it is not limited. I do not want to undermine the work of the digital designer. They are actually dealing with huge complexities, but they are mainly interested in few parameters. But I will give you in the next slides the list of the analog design parameters for only a one circuit, and you will see you have to deal with really many parameters at the same time for the same circuit. That makes your life complex, and and because there are many parameters, there are multidimensional trade-offs which are appearing in the scene. And then uh, digital designer may start his life from the gate level or the cell level libraries, but for the analog engineer, you have to have the good understanding of devices, particularly biasings, because almost all analog designs live upon feedback and they live upon biasings. Biasing theory is also very fundamental theory, just like feedback theory. And modeling. So you have to have a good understanding of modeling. Now, coming to robustness, as I talked earlier, robustness means have you checked your circuit with respect to process, voltage, temperature, radiation, and maybe if you are having any other variable which is your variable in your operating conditions. And then layout effects. These are quite detrimental. Layout effects are much severe in the analog design. And substrate effects, we talked of the integrated circuit design where everything is made on one substrate, which is silicon. It's good. You could reduce the size of your chips. You could cram many chips in a one circuit, and you could have gadgets like very modern digital devices. But the penalty you have paid is that by bringing all the things on a one substrate, they are actually interfering with each other. Had they been on the PCBs, the interference was not that severe, but they are so close, they are on a silicon, and from the silicon, the communications are happening between the digital area of the circuit and the analog areas of the circuit, and maybe vice versa also. And that involves understanding how to kill this mixed signal interference is another area which is quite a big area to understand. And analog design always will remain highly analytical. These are the list of the parameters. Many parameters I was talking of. Just see op-amp. If you really design op-amp, you have to deal with all these parameters. You have to at least give consideration to parameters in the beginning when you are taking up the op-amp design. Normally we talk of gain and unity gain bandwidth and maybe settling times, slew rates and phase margins, and it is over. Maybe input common voltage range. But no, you have to deal with the last figures also. The power, PSRR, CMRR, input equivalent noise voltage, everything almost. Now, these many parameters with the maybe 13 transistor circuits, maybe 20 transistors, 7 transistor circuit is a tough thing. Then you have to focus upon every transistor and its properties. Okay, robustness, radiation effect we have already talked of. Highly analytical, it's quite easy to understand. It is know-how based, it is application based. Yeah, this is one more area. You have to cleanly understand your application. For many years, I was thinking that designs are made even without the consideration of your loadings, because many books are not writing straight those things. And no, you have to sync your designs with your applications. That means you have to first understand your application environment nicely, cleanly, and in details. And then only start thinking of making your designs. Hand-based analysis, as I told, paper pencil approach, it will not be easy. It is not easy to take it off. Computer-based and okay, testing methodology. Testing methodology is the thing which we think very late. But it should be our habit to ultimately keep the testing in view while we are designing the circuits. One day they will come out from the fab and they will go through the testing. Okay, in that way I can give you the complete chain. You design the circuit, masks are made, they go to the fabrication house, they come out from the fabrication house, they go through initial ET parameters, electrical test parameter checkings, and then they come to the testing floor on wafers. Testing floor test it, they dice it, they cut the wafers, they pack the dice, again check it, again test it. Then also it is not end. They go through the qualification procedures, which are again subject them to the high temperature variations, subject them to the radiation, subject them to the environmental variations, which are maybe even saline waters, and then saline environment, sorry, and then the testing is really complete. I should write the word testing and qualification, both. I can give you an example of operational amplifiers as such. Now I will take you little through this procedure, not much, but because we all are familiar, because it's an analog design lecture. So I'm taking the case of an operational amplifier where we are very clean that VO is proportional to V2 minus V1 and multiplied by the differential gain. But there remains a question here. Do you think that this equation is complete? Books often write like that, but good books do not. What they do, they also add the term AC gain, which is the common mode gain. Now, what is the common mode gain? This gain which we are talking is the differential gain. The common mode gain is when both V1 and V2 are varying in sync. When both are increasing by the same amount, both are decreasing by the same amount. Then what is happening on the VO? Now, ideally, if you see, when V1 and V2 both are changing either upward or downward, nothing should happen on the VO. This comes from the property of op-amp, but in real life, there is a movement of VO with respect to common mode change in the V1 and V2. The equation says it's a differential change, which is V2 minus V1. The difference between the two is should be amplified, but the common signal is also amplified. So this equation is not complete in that sense. Now another area, I have not shown the power supply voltages. So there will be one positive supply, maybe 3.3, 1.8 volts, and there will be definitely a 0 volt. Now bipolar circuits are very rare. If you read the old books, they will show you plus 5 minus 5, plus 10 minus 10. But nowadays, it's almost a unipolar circuits we are making. The ground rail is 0, and upside we are dealing with maybe 3.3 volts or 5 volts or 1.8 volts, or even we have come to the levels of 1.2 volts. Maybe even they are predicting about 0.6, 0.7 volts things. Now, power supply variations will also disturb the output. So be careful. Equation looks very simple, but output is subjected to many changes because of many areas. One is the common mode change, other is the power supply changes. So your life is becoming complex. Even with this symbol, you should be aware of that the aim is VO should only change with V2 minus V1. Okay, parameters of this op-amp. Okay, I will just pass through it, but see the third parameter, CMRR. It is the ratio of differential voltage gain to common mode voltage gain, and this should be very high for your op-amp. Otherwise, your op-amp is also responding to the common mode voltage changes happening at the input. From where those changes are coming actually? This is an important question. See, why we are saying that V1 and V2 both can move. They can move intentionally also, they can move unintentionally also. When they move unintentionally, what is happening? The op-amp is lying nearby to, let us say, a digital block. And this digital block is running at very high speed. This digital block is passing its interference to the substrate, which is a silicon substrate. Op-amp, because it is lying nearby, it is picking that interference on both the pins, that is V1 and V2. So same disturbance is appearing on V1 also, V2 also. Common mode, it becomes in nature, but VO changes. And this is a problematic case because VO was to be clean. This is also important. The first one, you see, input common mode range. Range of voltage is applied to input in common mode fashion for the op-amp to operate within specifications. What does it mean is, when you are designing an op-amp, I told to you that do think of your environment and do think of your application. If your application is demanding that your op-amp should work from 0 volt to 1 volt, architecture may change. If it is demanding your op-amp should work from 1 volt to 3.3 volts, architecture may change. So your choice of architecture is dictated not only by the parameters but also operating conditions, operating environments and applications. What we really require in ideality. In ideality, this should be the case. It should be differential gain infinity and common mode gain I have written 0. So CMRR, which is first divided by second, differential by common mode, should be infinite. Input resistance, input common mode supply range, and output voltage range also supply range. Now the challenge is here only. We all know that this is the ideal condition of an op-amp. But my point is, can you come near to this ideality? Then you will feel the heat of the design. It's you know 3 things you can bring to ideality, and you will find that 5th or 6th or maybe some other is sacrificed. Why I have written output resistance in the other color is that let us distinguish between op-amp and OTA. Now this is a gray area where op-amp, as we read it from the college days, and it was not wrong, op-amps are supposed to give a very low output resistance. But what about OTS, operational transconductance amplifiers? They are not supposed to give the low output resistance. They are supposed to generate a current as the output. They are not supposed to generate voltage as the output. Anything where the current is output, output resistance should be very high. The reason being, otherwise current will be taken in its own resistance. You have to deliver the current to outside world. So OTAs are basically transconductance amplifiers. Transconductance means I am converting the voltage into current. It is I upon V. Op-amps are voltage to voltage converters or amplifiers, and they are V upon V. Now output resistance is one such important thing which distinguishes the op-amp from the OTA. Now the op-amp block diagram will look like this. We all know, anybody who has designed this concept, differential amplifier, second stage, output stage amplifiers, these are the things which are there in the op-amps, and the bias blocks, of course. Now this bias block is not I have shown it like this, but bias block is actually a very tough block to design, and half of your problem will be here only. And then imagine that you have to generate all the nice properties written in this slide. So I have just categorized OTA block. Okay, OTS. Why I have stopped focusing upon op-amps? The reason being, now this is an important area. Should I design an op-amp or should I design an OTA? Given that you are designing something inside the chip, CMOS circuits do not load anything which is in the which is driving it. Do not load anything means they do not load it in the DC fashion. They are having the capacitors as their inputs. Capacitance is the main thing on the gate. No DC current is taken. So that means whatever drivers you are making, whether in the digital side or in the analog side, your loading condition is actually capacitive in nature. Your loading is not resistive in nature. Had your loading been resistive in nature, your current would have been continuously going out or coming in. Capacitive loading means I have to drive it, I have to charge it, over. The point is, uh, because your load is capacitive in nature, you are basically dealing with a load where the high output resistance even can live with. Because at the end of the day, capacitance is open thing. So if I have to drive an open thing, I can drive it even with the high resistance. So why to make one more stage, which indicated in this slide, in the last stage, which is output stage amplifier, and written on the top, output resistance should be very low. So you see, we have not gone so far in any design process. We are only dealing on the block diagrams. But understanding of the whole scene is important so that you may decide whether you require op-amp or whether you require OTS, and books, therefore the CMOS electronic books deal with the OTA much more than op-amps. Okay, what is I have only listed the two practical problems which you are going to face in your op-amp designs, and offset is one such problem. The implications are high for this offset, and on the middle paragraph it is written, DC offset arises due to unavoidable mismatches in input differential stage of amplifier. This is important. Uh, you have okay, I have a schematic for that. I am going first on the schematic, and then only you'll see the schematic first. Now this is a differential amplifier, and think of transistors M2, M3, M4, M5. M2, M3 transistors are supposed to be same. M4, M5 are also supposed to be same. Now if they are not identical, if they are not same, the thing which you are going to suffer is the offset. So the message is, because we cannot deal with the circuit analysis, but the message is that analog design, where it is a default assumption is made that things are identical, but as I said to you, things vary from fab to fab, lot to lot, wafer to wafer, die to die, and inside die. That is, even up to the transistor to transistor it varies. So capturing of that variation is very important, because suppose you simulate this circuit without thinking of this mismatch which is inherent between M2, M3 or M4, M5, you will have no offset. But when this will come out, it will have the offset of somewhere in the range of 5 millivolt to 10 millivolts, plus minus. Why offset is plus minus? Because it can go in the other direction, positive direction also, negative. It is unpredictable thing. It depends upon the fabrication condition. Therefore, it is random, and therefore you have to treat it as a random thing. Now, then what? I have 5 millivolt offset. How it matters to me? See, if you have to amplify a signal of 1 millivolt, 5 millivolt offset matters to you. So you have to design the op-amp which is having a very low input offset voltage. So you think your life is over, but you come to this slide again. You have to design an op-amp with the low input offset voltage. Input offset voltage was appearing somewhere in the last, towards the last, after output resistance, input offset voltage. It comes there, but still that tough thing remains. Input offset voltage temperature coefficient. Now the funny thing is, not only this is a one-time offset, but this offset is showing a behavior of change with respect to temperature. So that means if the chip was today at 27, tomorrow it goes to 127, 100 degrees centigrade change, and suppose the offset temperature coefficient is, let us say, 100 microvolts per degree centigrade, 0.1 millivolts. So it has 100 into 0.1, 10 millivolt has further been added on it. So that is the problematic scene. Yeah, and okay. DC offset can also, yeah, it is ultimately the determiner of resolutions, and ultimately it reduces your signal operating range also. Coming to another important area of the slew rate. When you design an op amp, I'm not saying you have to deal with two parameters, but I'm saying what I want to highlight is that every parameter has its own effect, its own cause. You have to isolate the cause, the effect, and deal with it, and then you will feel the trade-off. One parameter says one parameter says increase the uh, one parameter says that increase the GM of your transistors, other says decrease the GM of your transistors. Then it is a tough thing. And you see this slew rate thing. Okay, we know the definition of slew rate. Put the op amp in the buffer fashion, change a voltage at the input, that is positive input, and you are going to have this type of output. This is strange because it didn't change that instantly, the input changed. Why? There is a reason behind it. Okay, as I have written, slew rate is maximum rate of change possible at the output of op amp. Now, slew rate give rise to specification called full power bandwidth, which is, if you go through any basic book, you will see if I give a sine wave to this op amp, V sine omega t, I differentiate it. What is I'm interested in finding the maximum rate of change of sine wave. Maximum rate of change of sine wave comes out to be SR is equal to W into V, omega into voltage. Now, I know this is the maximum rate of change of my input. Now, if it is maximum, at least my slew rate should be greater than this if I have to process this sine wave. Otherwise, slew rate will distort the sine wave. It will produce the distortion in my output. That is the full power bandwidth. Now consider this circuit, which is what differential. Yeah, it is a differential amplifier, and this is a very famous circuit. Why I am saying is that you will see if you design any amplifiers, which is much chunk of your analog work, you have to understand this circuit. Not only this, there is a circuit after this which is a second stage amplifier. Even if you start designing an operational amplifier, you will have a much understanding, much confidence of designing even bigger circuits. So start, this is a good point to start. And the bias circuits are another important area. Current mirrors, which you see in the form of MB and M1, the last last transistors below transistor MBM1, they are also an important area, current mirrors. Now I stop here, and I want to say that M2, you see these transistors M2 and M3. First of all, transistors are 4-terminal devices. They are not 3-terminal devices. So that blue line of M2 and M3 is shown to be going to the ground, VSS. Now the question is, why this line is going to the ground? Reason is, these are the NMOS transistors which are made in the P substrate. We know from our basic theory that all NMOS transistors are made in the P substrate, and P substrates ultimately will go to ground. Now, if I am making a chip where my substrate is P type, ultimately it is electrically connected to the ground, whether it is P well or it is P substrate. That means I have no other option left but to take this fourth terminal, which is the body terminal, to ground. But suppose I talk of the dual of this circuit. Dual of this circuit means the inputs are PMOS. Then you have an option. PMOS will be made in the N-wells. N-wells can float. Float means need not to connect to the highest potentials. That time, these M2, M3, had it been the PMOS, their body could have gone to the common source terminal, which is point number 2 here. So there you would have a choice, and that choice does make a difference in the ICMR. If you read the Alan Hallberg, it is given that what are the trade-offs involved of connecting for the PMOS body to its own source or body to VDD. PMOS body will go to the highest potential of that transistor. So either to source or even higher than that, which is VDD. Now consider, now okay, we talked of slew rate. Now consider this phenomena of slew rate. Assume that V2 is jumped. V2 is jumped means all current has been taken by the V2. Why? Because V2 is having the VGS very high as compared to M3, which has been not shown here. So M3 goes in the cutoff. M2 is carrying the complete bias current, which is I1. So I1 shifts to the left side completely, then it goes to the mirror. It gets mirrored from M4 to M5, and now where this I1 will go? Because M3 is off. So the current of M5, which is I1, ultimately has to go to the out. It will charge this capacitor. Now, you know, capacitor equation is basically dV by dt is equal to I by C. dV by dt is nothing but your slew rate, which is actually equal to I1 by C. Consider the other side. This is the analysis which we can even make on the copy. There is no analysis involved with respect to computer. And you see the other case. Now V1 has been jumped. So it takes the whole chunk of current, which is the bias current of M1, and M2 goes in off. Now what will happen? Mirror action, can it happen? M2 carries no current, it is off. M4 carries no current because nothing is coming from M2 side. There is a high resistance in this path. No current will flow in M4. If no current, then M5 is also cannot carry any current. Then the only current which M3 is carrying can come from out. So capacitor will start discharging by the same current, which is I1 by C. So in this way, slew rates are being decided. Had it been other, the second stage after this, even then the equations would have been the same. You can judge it, and the one good book is Behzad Razavi. You do the slew rate analysis from Behzad Razavi is quite good. This is that second circuit, and this is how we are proceeding for the bigger circuits. Even bigger than this. This is not a bigger circuit actually. This is quite a simple circuit, but you can go for the switched capacitor circuits. If you understand this OTS, if you understand the charge movements, then switched capacitor circuits can be designed, and even the big voltage regulators analog designs can be taken care of. Yeah. And with this, okay, I have few simulated waveforms. This is of one circuit which I was designing, and why I have brought it here is because everybody talks of the nicer things, the gain, the full, the bandwidths, the UGBs, but very difficult to talk of power supply rejections. Power supply rejections is a phenomena which are taken as the second order phenomena to be considered at the end of the back of the envelopes or something like that. But not so. Power supply rejections can ultimately, if they are not good, they can kill your circuits. So here if you see that circuit was actually changing from no load to full load conditions, and in the no load conditions you are getting the power supply rejections below 100 Hz, somewhere in the range of 80 or maybe 78 dB. Sorry, 68 dB. And in the full load you will get it somewhere in the range of 58 dBs. And then both are falling, then both are increasing. Now, should I leave this phenomena of falling and increasing as something just happening? But people have even analyzed why this is happening. And pole and zeros concepts become ultra important at that juncture. So analog design starts becoming tough, and the reading and then much is required. Even your simulations, even your strategy of simulations. So be careful of all these things. And even if you think that analog is so tough, or everybody talks of like that, so why not to move to digital? Let me tell you, digital is also extremely tough. When you talk of gigahertz, it's not easy to build a processor of gigahertz region. Even I have seen a chip where the temperature variations inside the chip, temperature variations are 40 degrees centigrade. Just a 10 mm by 10 mm sort of chip. It can be so. Clock trees are not easy to build. You see, we do not talk of temperature coefficients. We do talk of this type. This is a band gap circuit curve, the famous curve of the band gap circuit. And in the last, I have shown you something of over temperature protection, where I want to show that even the hysteresis concept is to be really analyzed. And it is a case of hysteresis. Actually, the second curve is cutting the first one, and around it is hysteresis. So falling and the rising is happening at the different temperatures. So this type of circuits are required for the over temperature protection areas. Yeah, this is over for me. Thank you for your listening, for your patience.
Any query from any of the nodal centers? Any question? Jammu. Any query at MIT Jammu? Institute of Engineering and Technology. No question? Nice, sir. Thapar Polytechnic. Any question? Thapar Polytechnic. Sukhmani College, SSIT, Derabasi. Any SGT Gurgaon. SGT Gurgaon, sir, do you have any query? Atharva College. Any question? Yes, ma'am, do you have any query? Your mic is on.
So thank you so much,
Yeah,
sir, for
thanks.
sharing your valuable knowledge with us.
Yeah, thank you very much.
We will start with our next session, my short